In the outer reaches of the solar system, beyond the frost line where sunlight fades and water turns to stone, lie worlds that should be dead, yet whisper of hidden oceans. Beneath their cracked and gleaming surfaces, the moons Europa, Enceladus, Titan, Ganymede, and even distant Pluto conceal liquid water oceans sealed under kilometers of ice. The discovery of these subsurface seas, vast, global, and enduring, has transformed our understanding of habitability. Where we once imagined life confined to warm, sunlit worlds, we now find that it may flourish in darkness, warmed by tides and geology rather than starlight. The ice-covered moons of the outer planets are no longer frozen relics. They are living laboratories challenging every assumption about where life can exist. The origins of the idea. Clues from Voyager. The story of the ocean worlds begins in the late 1970s with NASA's Voyager 1 and Voyager 2 missions, whose twin spacecraft swept through the Jovian and Saturnian systems. Their images of Europa astonished scientists. A smooth, bright surface, crisscrossed with dark lines, fractures and ridges stretching for thousands of kilometers. Unlike the heavily cratered terrains of other moons, Europa's face was young, resurfaced by some unknown process. The lack of craters suggested geological activity, implying that the interior could be warm and dynamic, despite the sun's faint glow at that distance. Some planetary scientists, notably Richard Greenberg and Cynthia Phillips, proposed that Europa's smooth plains were frozen oceans, a thin crust of ice floating atop liquid water. Voyager's brief glimpse was enough to plant a revolution. If a small moon like Europa could maintain internal heat and liquid water, it meant that tidal forces from its parent planet could generate more energy than sunlight ever could. Similar reasoning began to apply to other moons: Ganymede, Callisto, and especially Enceladus, the small but active satellite of Saturn, whose surface showed suspiciously smooth regions amid cratered ice. The Voyager data hinted at something profound. The solar system was more alive than it looked. Galileo and the confirmation of an ocean. 2 decades later, the Galileo spacecraft provided the evidence Voyager had only hinted at. Orbiting Jupiter from 1995 to 2003, Galileo carried instruments capable of measuring magnetic fields and gravity. When it flew past Europa, it detected an induced magnetic field that fluctuated in sync with Jupiter's powerful magnetosphere, a signature consistent with a conducting layer beneath the surface. The only plausible conductor was salty liquid water. Combined with measurements of Europa's density and surface composition, this pointed decisively toward a global ocean, tens of kilometers below the ice, containing more water than all of Earth's oceans combined. Galileo's imagery reinforced the case. The surface showed chaotic terrains, jumbled blocks of ice frozen mid-motion, as if massive slabs had broken, drifted, and refrozen atop a mobile layer below. In regions like Connemara Chaos, surface plates the size of cities appear to have rotated and refitted like a puzzle, their edges filled with refrozen slush. This pattern mirrors pack ice on Earth's polar seas. Such behavior cannot occur on a static crust. It requires a lubricating layer of liquid water. Europa, it seemed, was not a solid world at all, but a thin shell of ice floating on a deep ocean, warmed from below by the rhythmic flexing of Jupiter's tides. Enceladus, the surprise at Saturn. If Europa revealed an ocean by inference, Enceladus revealed it directly. When the Cassini spacecraft arrived at Saturn in 2004, it found Enceladus to be geologically active, with geysers erupting from fissures near its south pole. The region, dubbed the Tiger Stripes, emitted plumes of water vapor, ice grains, and organic molecules hundreds of kilometers into space. Cassini's instruments flew through these plumes, sampling their composition. They contained salty water, carbon dioxide, methane, ammonia, and complex organic compounds. Unmistakable signs of a subsurface ocean in contact with rock. Further analysis indicated hydrothermal activity at the sea floor, where water interacts with a silicate core, producing heat and chemical gradients capable of sustaining microbial ecosystems. In an instant, Enceladus joined Europa as a prime candidate for extraterrestrial life. The plumes also solved a mystery. Saturn's E-ring, a diffuse ring of microscopic ice particles, is continually replenished by Enceladus's emissions. The Moon, though only 500 kilometers wide, acts as a natural cryovolcanic engine, venting an interior ocean through cracks in its icy crust. Measurements of gravitational variations revealed that the ocean is global, about 30 to 40 kilometers deep, lying beneath an ice shell that thins dramatically at the poles. In contrast to Europa's hidden sea, Enceladus's ocean announces itself in glittering fountains visible from space, a cosmic beacon of habitability. Beyond Europa and Enceladus, a family of hidden seas, once scientists accepted that oceans could exist beneath ice, they began to find them everywhere. Jupiter's Ganymede, the largest moon in the solar system, shows evidence of multiple layers of liquid water sandwiched between ice phases, maintained by pressure and salt. Even Callisto, long thought inert, may possess a deep, slushy ocean. Moving outward, Saturn's Titan, larger than Mercury, hides a subsurface ocean of ammonia-rich water beneath its hydrocarbon lakes and dunes. The dwarf planet Pluto, revealed by New Horizons in 2015, likely retains a liquid layer beneath its nitrogen ice crust, sustained by radiogenic heat. Neptune's moon Triton, and even some Kuiper Belt objects, may host similar internal seas. The discovery of one ocean world became the discovery of many. What was once a singular miracle turned out to be a common planetary pattern. The implication is staggering. In the classical habitable zone model, life is possible only where starlight maintains liquid water on a planet's surface. But ocean worlds defy that rule. They are habitable from within, powered by internal heat rather than solar energy. This expands the potential real estate for life by orders of magnitude. In our solar system alone, there may be 10 times more habitable oceans under ice than on Earth's surface. The cosmos, it turns out, hides its life not in sunlight, but in shadow. Evidence from magnetism, gravity, and topography. The detection of subsurface oceans relies on indirect but converging lines of evidence. For Europa and Ganymede, the key is magnetic induction. Variable magnetic fields measured by spacecraft as they pass through the planet's magnetosphere. Conductive layers, such as salty water, respond to these fluctuations, revealing themselves through secondary magnetic signatures. Gravitational measurements from spacecraft tracking reveal mass distributions consistent with differentiated layers, ice above, liquid below. Surface topography, particularly the flexing of the crust under tidal forces, further constrains ice thickness. On Europa, models suggest an ice shell 15 to 25 kilometers thick, over a 100-kilometer deep ocean. On Enceladus, the ice may be as thin as 5 kilometers near the poles, where geysers erupt through fissures kept open by tidal stress and heat dissipation. Spectroscopy adds another layer of proof. The detection of sodium salts, carbonates, and organics in the ejecta of Enceladus and the surface of Europa confirms chemical exchange between the oceans and crust. In essence, these worlds communicate. Their oceans vent to space, their surfaces recycle, and their interiors evolve dynamically. This circulation means that even without sunlight, materials and energy flow, the two prerequisites for life's metabolism. The new paradigm, life beyond the habitable zone. The recognition of subsurface oceans marks a paradigm shift as profound as the discovery of exoplanets. It dissolves the notion that habitability is confined to a narrow orbital range. Instead, it reveals that the habitable zone extends wherever energy and water coexist, even beneath miles of ice in eternal night. If hydrothermal vents on Earth's ocean floor teem with life independent of sunlight, why not Europa's? If microbes thrive kilometers deep in Antarctic ice, why not Enceladus's crust? The universe, it seems, is less about where life can exist and more about where it cannot. The boundaries are far wider than we ever imagined. In this new vision, the solar system becomes an archipelago of hidden oceans, each a potential cradle of biology. Earth is not the lone oasis, but part of a vast archipelago of water worlds, each governed by its own balance of heat, pressure, and chemistry. Some, like Europa, may host deep, dark oceans under thick shells. Others, like Enceladus, vent their interiors into space. Titan, with its methane rivers and nitrogen atmosphere, adds an entirely new chemistry, organic, alien, yet tantalizingly familiar. Collectively, these worlds challenge the anthropocentric assumption that life must look like ours or live as we do. A universe of oceans. The lesson from these discoveries is humbling. Oceans are the cosmic norm, not the exception. Water, in its solid or liquid form, pervades the outer solar system. If liquid layers can persist beneath ice on moons, no larger than continents, then throughout the Milky Way, among the billions of icy exoplanets orbiting dim stars, the number of hidden oceans may be beyond comprehension. The ocean worlds are teaching us that life's domain is far broader than sunlight's reach. The frontier of astrobiology now lies not in deserts or atmospheres, but in the depths of alien seas, warmed by the quiet tides of distant giants. And so, as the ice moons circle their planets in eternal twilight, they embody a new definition of habitability, one that unites water, chemistry, and energy, independent of sun and sky. They remind us that the cosmos is not a frozen void, but a hydrosphere in waiting, and that even in darkness the potential for life endures. The discovery of these oceans has changed more than planetary science. It has redefined life's geography. In the frigid darkness of the outer solar system, volcanoes still erupt, not with molten rock and sulfurous fire, but with ice, vapor, and salt water. This astonishing phenomenon, known as cryovolcanism, defies every expectation formed from our terrestrial experience. On worlds like Europa, Enceladus, Titan, and even distant Pluto, cold replaces heat, and water becomes the analogue of lava. Through cracks in ice crusts, these moons exhale plumes of vapor and crystalline frost, venting the breath of hidden oceans into space. Each eruption carries a chemical message from the deep, revealing the interplay between energy, water, and organic chemistry, far from the sun's warmth. Cryovolcanism is, quite literally, the pulse of ocean worlds, their way of telling us they are still alive. To understand cryovolcanism, we must first redefine what a volcano can be. On Earth, volcanic activity arises from the melting of silicate rocks and the ascent of magma through fractures to the surface. In the outer solar system, temperatures are so low, often below -180 degrees Celsius, that silicate rock remains eternally solid. Yet volatile compounds like water, ammonia, methane, and carbon dioxide behave differently. Under pressure, these ices can melt, forming slurries or liquids that, when released, behave just like terrestrial lava. They erupt through fissures, floodplains, and refreeze as smooth surfaces. The physics is the same. Buoyant material from below rises through a brittle crust, driven by internal energy gradients. The only difference is composition. ice replaces magma, and sublimation replaces incandescence. The energy source for such eruptions is primarily tidal heating, the flexing of a moon's interior under the gravitational grip of its parent planet. As Europa or Enceladus moves in an elliptical orbit, it is alternately stretched and compressed, generating frictional heat in its interior. This heat melts subsurface ice, sustaining oceans and pressurizing pockets of water. When fractures open to the surface, the result is an eruption. Jets of vapor, ice grains, and salts propelled into space at hundreds of meters per second. In the vacuum, liquid instantly vaporizes and refreezes, producing plumes that can extend hundreds of kilometers above the surface. Spectacular geysers in slow motion. The most dramatic example of cryovolcanism comes from Enceladus, Saturn's shimmering snow-white moon. Before the Cassini spacecraft arrived in 2004, Enceladus was considered geologically inert. Then Cassini's cameras revealed the truth. From the moon's south pole, enormous jets of water vapor burst through 4 parallel fractures, the now famous tiger stripes. Against the black of space, sunlight illuminated the sprays like frozen auroras. These plumes, reaching 500 kilometers high, were not occasional events but continuous eruptions, sustained for years of observation. Cassini's instruments flew directly through them, tasting their composition. What they found revolutionized astrobiology. The plumes contained water vapor, ice particles, carbon dioxide, methane, molecular hydrogen, and ammonia, along with complex organic molecules up to several hundred atomic mass units. Crucially, the detection of hydrogen gas, H2, indicated ongoing hydrothermal reactions within Enceladus's rocky core. On Earth, similar reactions at mid-ocean ridges sustain rich ecosystems independent of sunlight. The chemistry implied that liquid water in contact with rock was producing energy through serpentinization. The alteration of olivine-rich rock by water, releasing hydrogen that microbes could use as fuel. In other words, Enceladus possesses all 3 pillars of habitability: liquid water, energy, and chemistry. Subsequent measurements strengthened this picture. Gravitational mapping revealed a global subsurface ocean about 30 to 40 kilometers deep. The composition of the plumes matched salts and silica, expected from hydrothermal vents. Tiny silica grains detected by Cassini's dust analyzer pointed to high-temperature interactions greater than 90 degrees Celsius between water and rock, far warmer than passive melting could produce. Enceladus, it turned out, is not just an icy shell over a frozen core, but a planetary laboratory of chemistry, where geology and ocean intermingle through vents miles beneath the ice. Europa's elusive plumes. If Enceladus is the showman of cryovolcanism, Europa is the enigma. Its plumes are less spectacular, more intermittent, but no less intriguing. The Hubble Space Telescope, observing Europa in ultraviolet light in 2012, and again in 2016, detected transient features at the moon's limb. Faint curtains of water vapor extending up to 200 kilometers high. These emissions coincided with regions of known surface fractures, particularly near the equator, and varied in intensity over time. Additional evidence came from reanalysis of Galileo data. As the spacecraft passed through Europa's magnetic environment in 1997, it recorded fluctuations consistent with a plume interacting with Jupiter's magnetosphere. Decades later, those archived readings took on new meaning. Galileo may have flown directly through a Europan eruption without realizing it. Unlike Enceladus, Europa's plumes appear sporadic, possibly triggered by tidal stresses that open and close surface cracks as the moon orbits Jupiter. The cryovolcanic mechanism likely involves pressurized reservoirs of water within the ice shell. Not as direct as Enceladus's venting from the global ocean, but still capable of transporting interior material to space. If confirmed, these plumes would provide access to Europa's hidden ocean without the need to drill through kilometers of ice. Future missions, including Europa Clipper, aim to fly repeatedly through suspected eruption zones, sampling the expelled material for signs of organic chemistry or microbial life. The plumes of Enceladus and possibly Europa act as natural probes of their subsurface oceans. Each molecule they release is a messenger from environments we cannot yet reach. Their chemistry offers a window into the balance between oxidants and reductants, the same chemical tension that fuels metabolism on Earth. For example, the hydrogen in Enceladus's plumes suggests active serpentinization, while the presence of carbon dioxide and methane indicates ongoing carbon cycling. Together, these imply chemical disequilibrium, the very condition that life exploits to extract energy. Organic compounds detected in the plumes span a wide range, from simple hydrocarbons like methane and ethane, to complex organics resembling amino acid precursors. Some are associated with salt-rich ice grains, hinting that they originate in the ocean rather than from photochemical reactions at the surface. The ratios of these molecules offer clues to the ocean's pH, salinity, and redox state. Enceladus's ocean, for instance, appears to be mildly alkaline, pH 9 to 11, similar to terrestrial hydrothermal systems that host thriving microbial communities. This environment could support methanogenic archaea, organisms that produce methane by combining hydrogen and carbon dioxide, a process mirrored in Enceladus's own emissions. For Europa, surface chemistry adds another layer of complexity. Its crust is bombarded by Jupiter's radiation, producing oxidants like oxygen and hydrogen peroxide. If these oxidants reach the ocean through cracks or brine channels, they could balance the reductants from hydrothermal activity below, creating a redox gradient ideal for life. The plumes, in this case, might represent more than geological leakage. They could be breathing cycles, the planet's equivalent of respiration. Cryovolcanism beyond the gas giants. While Europa and Enceladus dominate discussions, cryovolcanism extends to other worlds as well. Titan, Saturn's largest moon, shows evidence of cryovolcanic domes and flow features, possibly driven by mixtures of water, ammonia, and methane. Cassini's radar imaged mountains and Labat flows that resemble volcanic deposits, and its infrared instruments detected transient clouds of methane consistent with active outgassing. On Triton, Neptune's captured moon, Voyager 2 photographed geyser-like plumes of nitrogen gas rising from sunlit regions, driven not by tidal heating, but by seasonal solar warming of dark surface patches. Even Pluto, at the edge of the solar system, exhibits enormous ice volcanoes such as Wright Mons, whose morphology suggests recent eruptions of ammonia water slurry. The common thread is unmistakable. Volcanism, in one form or another, is universal. Even in the coldest environments, planetary interiors find ways to vent energy to the surface. Cryovolcanism matters not merely as geology, but as biology's potential gateway. On Earth, hydrothermal vents are cradles of life, ecosystems sustained by the same processes driving cryovolcanic activity on ocean worlds. The plumes of Enceladus and Europa may carry organic material, or even microbial cells ejected from deep hydrothermal environments. Because the plumes vent directly into space, they provide a rare opportunity to sample an alien ocean without contamination. Instead of drilling through ice, spacecraft can simply fly through the vapor and analyze its chemistry. In this way, cryovolcanoes are nature's delivery systems, bringing the secrets of the subsurface to our instruments. Each eruption is a data stream, a living experiment broadcast across the void. The possibility that such plumes contain biological material is no longer science fiction. Cassini's detection of complex organics, including carbon ring structures and nitrogen-bearing molecules, demonstrates that prebiotic chemistry is active in Enceladus's ocean. If microbes exist there, they might be expelled in frozen droplets, preserved in the cold vacuum until collected by spacecraft sensors. Future missions equipped with high-resolution mass spectrometers will test this idea directly. A single microbe, detected and confirmed, would change our understanding of life's universality forever. Cryovolcanism also serves as a mechanism for planetary renewal. On Earth, volcanism recycles nutrients and gases between crust and atmosphere. On icy moons, cryovolcanic plumes perform a similar function, transferring materials between ocean, crust, and space. This continuous cycling prevents chemical stagnation and maintains the disequilibrium necessary for habitability. The resurfacing observed on Europa, the absence of old craters, the presence of young ridges and chaos terrains, reflects an active crust continually reshaped by internal processes. Enceladus's persistent plumes show that even a small body can sustain geological vitality for billions of years when powered by tidal resonance. These moons are not frozen fossils, but living systems, their ice crusts the equivalent of breathing skin. Cryovolcanism redefines our conception of the vital planet. It proves that geological activity is not limited by temperature, that cold worlds can be as dynamic as warm ones, provided they have internal energy and volatile reservoirs. It also demonstrates that life need not require sunlight or even atmosphere. On Enceladus and Europa, the crucial ingredients are confined and conserved, shielded from radiation, stirred by tides, and released through plumes that act as natural messengers. In this framework, the search for life becomes less about temperature and more about energy flow, the universal metric of vitality. The icy moons, through their geysers and fractures, show that even at negative 200 degrees Celsius, planets can still breathe, evolve, and exchange materials with their environment. Cryovolcanism is not an anomaly. It is the natural expression of thermal balance in cold systems. It bridges the gap between geology and biology, linking the deep physics of tides with the delicate chemistry of prebiotic molecules. In these frozen eruptions, we glimpse a cosmos alive with quiet activity. A universe where even ice has a heartbeat. And so, when the next spacecraft sails through the plumes of Europa or Enceladus, it will not simply collect data. It will be listening to an ocean speak. Every molecule of vapor, every grain of ice, carries a story from a hidden sea. Stories of heat in the cold, of chemistry in the dark, of possibility in the silence. Cryovolcanism is the poetry of frozen worlds, written in vapor and light, reminding us that life's language may be universal, even when whispered in ice. Life, wherever it exists, requires one fundamental ingredient above all others: energy. Without it, chemistry stagnates, metabolism ceases, and time becomes still. On Earth, sunlight powers nearly every ecosystem, driving photosynthesis, weather, and climate. But in the outer solar system, where sunlight dwindles to a faint glow and temperatures plunge below -200 degrees Celsius, a different kind of energy reigns, one born not of radiation, but of motion and decay. The oceans of Europa, Enceladus, and their kin are sustained not by starlight, but by tidal heating and radiogenic warmth, invisible forces that turn darkness into dynamism. These internal fires of ice worlds illuminate a new paradigm of habitability. That energy can arise from within, and that life need not orbit a star to endure. The physics of tides, gravitational sculptors of worlds. Tidal heating arises from a simple principle with cosmic consequences. Gravitational flexing. When a moon orbits a massive planet like Jupiter or Saturn, it is continually pulled by the planet's gravity. If its orbit were perfectly circular, the force would be steady, producing no heat. But if the orbit is slightly elliptical, the gravitational pull changes constantly, stretching and compressing the moon's body like a rubber ball. The friction generated by this internal flexing converts orbital energy into heat, warming the moon's interior. This process is not trivial. The heat produced by tidal flexing in Europa and Enceladus can exceed that of all radioactive decay combined. It is the same mechanism that powers Jupiter's volcanic moon Io, where tidal stresses melt rock into magma, producing the most active volcanoes in the solar system. On icy moons, the material is different, ice and water instead of silicate rock, but the physics is identical. The result is tidal melting, maintaining subsurface oceans over billions of years, despite the cold of space. Orbital resonance, the dance that sustains warmth. Tidal heating depends critically on maintaining orbital eccentricity, the slight elongation of a moon's path around its planet. Left alone, gravitational interactions would circularize the orbit, damping the flexing and ending the heat. But in systems like Jupiter's and Saturn's, groups of moons engage in orbital resonances that keep their orbits elliptical. Europa, Io, and Ganymede, for example, are locked in a 1 to 2 to 4 resonance. For every orbit of Ganymede, Europa completes 2 and Io 4. This rhythmic gravitational tug keeps their orbits eccentric, ensuring perpetual flexing and heating. In Enceladus's case, resonance with the larger moon, Dione maintains its slight orbital elongation. As Enceladus moves closer to and farther from Saturn, its icy shell and rocky core twist microscopically, generating frictional heat deep below. This energy powers the moon's global ocean and drives the spectacular geysers at its south pole. Without this resonance, Enceladus would freeze solid within a few million years. The heat it radiates, roughly 15 gigawatts comparable to Earth's geothermal output, is thus a cosmic dividend of motion, drawn from the gravitational energy of Saturn itself. The phenomenon reveals a profound truth about planetary systems. Gravity is not static. It is a continuous transaction of energy, converting orbital stability into geological vitality. Where planets and moons dance in resonance, life may find warmth even in the absence of a star. Alongside tidal heating, a quieter energy source works in the depths: radiogenic decay. Elements like uranium-238, thorium-232, and potassium-40 naturally release heat as they undergo radioactive decay. On Earth, this process powers mantle convection and drives plate tectonics. In icy moons, the same mechanism contributes a steady, low-level warmth that slows cooling and promotes differentiation. The separation of core, mantle, and crust. Although small compared to tidal heating, radiogenic heat plays a critical supporting role. It ensures that even isolated bodies far from giant planets like Pluto or Triton can retain internal liquid layers. Models suggest that radiogenic decay alone could maintain subsurface oceans tens of kilometers thick over billions of years if combined with insulating ice shells. On larger moons, such as Ganymede and Titan, the combination of radiogenic and tidal heat creates layered oceans, where high-pressure ice phases form between liquid layers, a complex multi-tiered hydrosphere sustained entirely from within. This internal heating is also self-regulating. As a moon cools, its ice thickens, increasing frictional dissipation under tidal flexing. The result is a thermal equilibrium, where heat generation balances heat loss, a planetary thermostat that can persist for eons. Such systems may represent the most stable habitats in the solar system, oceans sealed from radiation, immune to climate fluctuations, and powered by the fundamental constants of physics. The interplay of tidal and radiogenic heating determines a moon's internal architecture. The arrangement of its layers, the thickness of its ice, and the behavior of its plumes. In Europa, models indicate a rocky mantle heated primarily by tides, overlaid by a global ocean and a 15 to 25 kilometer crust. Thermal convection within the ice transports heat upward, driving surface cracking and resurfacing. At the ocean floor, hydrothermal vents likely form where tidal heat concentrates in the silicate mantle. These vents could generate steep chemical gradients, feeding potential ecosystems much like Earth's deep-sea vent communities. Enceladus, smaller and more flexible, shows a different balance. Its heating is concentrated near the poles, where the ice is thinnest. Cassini's observations revealed warm fissures radiating more heat than can be explained by uniform distribution, evidence of localized tidal dissipation, possibly amplified by resonant oscillations of the ice shell. The tiger stripes, therefore, are not merely cracks, but conduits of heat, connecting ocean and space. Through them, the moon expels its excess energy in geysers of vapor and ice, maintaining thermal equilibrium while revealing its inner life. Titan and Ganymede add further diversity. Titan's vast mass and thick atmosphere trap internal heat, while radiogenic decay and residual accretional warmth maintain an ocean of ammonia water mixture beneath its icy crust. Ganymede's immense gravity compresses its interior into multiple ice layers, separated by conductive liquid strata. Each world, governed by the same principles, finds its own balance between cooling and flexing, a harmony of heat that defines its habitability. For astrobiology, the significance of these heating processes lies in the creation of chemical disequilibrium, the separation of energy states that allows metabolism. Life, at its core, is the exploitation of gradients, thermal, chemical, or electrical. Tidal and radiogenic energy provide precisely these conditions. At the interfaces between hot rock and cold ocean, between oxidized surface ice and reduced interior, redox reactions flourish. Water-rock interactions release hydrogen. Oxidants from the surface deliver oxygen and sulfur compounds. Carbon-bearing molecules circulate between them. Together, these cycles mimic the foundations of Earth's biosphere. But on worlds with no sunlight at all, this realization broadens the definition of a habitable environment. A world need not orbit within the sun's traditional habitable zone. It need only sustain internal energy capable of driving chemical complexity. In this sense, Europa and Enceladus represent an entirely new class of biospheres, endo-oceanic habitats, powered from within rather than from above. If life can arise in such places, then the cosmos may teem with living worlds orbiting in darkness, planets adrift between stars, warmed only by radioactive decay and the memory of tidal motion. The universe's capacity for life may thus be far greater than the narrow annulus around each star once implied. Thermal evolution and longevity. The long-term evolution of tidal and radiogenic heating determines how long these oceans endure. In early epochs, moons experience intense tidal heating as their orbits settle into resonance, potentially generating magma or complete melting. Over time, as orbital energy dissipates and eccentricities dampen, heating stabilizes into steady maintenance levels. Radiogenic heat then becomes dominant, providing a slow decline rather than abrupt freezing. Current models predict that Europa's ocean could persist for billions of years, as long as Earth's biosphere, while Enceladus's smaller reservoir may eventually cool within hundreds of millions. Yet even that span is vast enough for evolutionary processes to unfold if life exists there. The persistence of internal heat also has geological consequences. Repeated cycles of melting and refreezing drive cryovolcanism, tectonic resurfacing, and chemical recycling, ensuring that no layer remains isolated. In this continual stirring lies the potential for complexity, for oceans that not only exist, but evolve, chemically and thermodynamically. The same feedbacks that sustain habitability on Earth through volcanism and tectonics operate in these ice worlds through tides and decay. Habitability, once again, proves to be a function of motion. Comparing ocean worlds highlights the astonishing versatility of energy systems in the cosmos. On Earth, solar and geothermal energies intertwine to sustain life. On Europa and Enceladus, gravity and radioactivity take over. On Titan, chemical and atmospheric cycles contribute additional warmth. Even on distant Pluto, residual radioactive heat may keep part of its heart-shaped basin liquid beneath kilometers of nitrogen ice. Each case reveals a different path to the same outcome, a dynamic equilibrium that defies the cold. This diversity also reshapes our search for exoplanets. Many of the billions of icy bodies orbiting gas giants throughout the galaxy may harbor similar internal heating. Even free-floating rogue planets, ejected from their systems, could retain subsurface oceans through radiogenic decay and insulating ice. The existence of energy, not proximity to a star, may be the true determinant of life's distribution. Mars, once warmed by volcanic and atmospheric heat, now frozen, and Europa, alive beneath its ice, define opposite ends of the same continuum, one where habitability migrates inward, from surface to subsurface, as worlds age and cool. There is something deeply poetic about the discovery that cold worlds can harbor fire within. It reverses our expectations, transforming desolation into potential. Europa and Enceladus show that warmth is not only a measure of temperature, but of activity, the restlessness of matter under gravity's rhythm. Where motion persists, energy flows. Where energy flows, chemistry awakens. Even in the most remote corners of the solar system, the laws of physics conspire to sustain the possibility of life. The ancient myths imagined warmth as divine, Prometheus stealing fire for humankind. In the cosmos, gravity itself is Prometheus, kindling heat in the hearts of frozen moons. These hidden fires remind us that the universe does not need sunlight to create vitality. It needs only imbalance, tension, and time. The same principles that stir oceans beneath ice may stir molecules toward consciousness elsewhere. In the end, tidal heating and radiogenic warmth are not mere curiosities of planetary mechanics. They are the heartbeat of the dark biosphere, the forces that turn sterile ice into living water. They demonstrate that energy, the currency of life, can take many forms and flow through unexpected channels. The icy moons of the outer solar system are not inert or forgotten. They are cosmic experiments in alternative habitability. Beneath their frozen faces, tides rise and fall, minerals react, and perhaps in some secret abyss, metabolism flickers. Through them we learn that life's flame need not burn bright. It need only burn steady. And as long as gravity pulls and atoms decay, that flame will never truly go out. When we imagine life elsewhere, we imagine chemistry, molecules forming, reacting, and self-organizing into something greater than the sum of their parts. For decades, astrobiologists have sought to understand where such chemistry could take root. The discovery of subsurface oceans on Europa, Enceladus, and other icy worlds changed everything. Beneath crusts of ice, tens of kilometers thick, lie vast oceans of liquid water, infused with salts, minerals, and organics. These are not sterile seas. They are chemical laboratories, operating in slow motion and utter darkness, where the building blocks of life assemble under pressures and conditions alien to Earth. The frozen seas of these moons hold the ingredients of biology: carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus, and the energy to rearrange them into complex forms. In the silence beneath the ice, organic chemistry is at work. The foundation of any living system lies in organic chemistry, the study of carbon-based molecules that can form chains, rings, and networks. On Earth, such molecules emerged from the primordial oceans through a combination of atmospheric reactions, hydrothermal synthesis, and extraterrestrial delivery by comets and meteorites. On icy moons, the process is both similar and different. Here, organics likely come from three major sources: inherited materials, endogenic synthesis, and external delivery. Inherited materials are primordial, the remnants of the solar nebula from which the planets formed. Carbonaceous chondrites, the primitive building blocks of these moons, are rich in amino acids. Polycyclic aromatic hydrocarbons, PAHS, and nitriles. During accretion, these compounds became embedded in the icy mantles of Europa, Enceladus, and Titan. Endogenic synthesis occurs within the moons themselves, where hydrothermal reactions at the seafloor or radiolytic processing in the ice create new organics from simple precursors. External delivery comes from micrometeorites and interplanetary dust, continually seeding the surface with carbon-rich material. Together, these processes ensure that even in the far reaches of the solar system, organic chemistry is universal. Cassini's analysis of Enceladus's plumes provided the first direct evidence. The spacecraft's cosmic dust analyzer detected large, complex organic molecules in the ejected ice grains, some exceeding 200 atomic mass units, consistent with carbon chains, rings, and aromatic structures. Many contained nitrogen and oxygen, suggesting a chemistry far beyond the simple methane and ammonia once expected. On Europa, the Hubble Space Telescope and ground-based spectroscopy have revealed similar surface organics: dark material coating ridges and chaos terrains, likely upwelled from the ocean below. In both worlds, radiation from their parent planets further processes these compounds, creating oxygenated and nitrated organics, much like early Earth's prebiotic soup under ultraviolet light. At the heart of organic production in ocean worlds are hydrothermal systems, where heated water interacts with rock. On Earth's seafloor, such systems sustain entire ecosystems, from tube worms to archaea, powered not by sunlight, but by chemistry. At vents like the Lost City hydrothermal field, alkaline fluids rich in hydrogen, methane, and minerals mix with cold ocean water, driving reactions that form amino acids, fatty acids, and simple sugars. The same processes could occur within the seafloors of Europa and Enceladus. When liquid water percolates through a silicate mantle containing minerals like olivine, it triggers serpentinization, a reaction that converts iron and magnesium silicates into serpentine and magnetite, releasing hydrogen gas. This hydrogen acts as a powerful reducing agent, fueling reactions with carbon dioxide to form methane and longer hydrocarbons. Laboratory simulations show that under high pressures and moderate temperatures, approximately 100 to 150 degrees Celsius, these conditions can spontaneously generate abiotic organic molecules. If catalysts such as nickel or iron sulfides are present, as they likely are, the efficiency of synthesis increases dramatically. Enceladus provides direct evidence of this process. Cassini detected silica nanoparticles in its plumes, a signature of high-temperature water-rock interaction. The presence of molecular hydrogen confirmed that serpentinization is ongoing. This means Enceladus's ocean is chemically active, continually renewing its inventory of organics. Europa, with its greater mass and higher tidal energy, likely supports even more vigorous hydrothermal circulation. Its sea floor could be studied with vent fields, each a potential crucible for prebiotic chemistry. If life exists there, it may owe its origin to the same hydrothermal alchemy that gave rise to Earth's biosphere. Radiation, paradoxically, is both a destroyer and a creator. On Europa, intense radiation from Jupiter's magnetosphere bombards the surface with electrons and ions, breaking molecular bonds and creating reactive species like hydroxyl radicals, ozone, and peroxides. While this environment would be lethal to surface life, it drives powerful radiolytic chemistry that continually generates oxidants. When these oxidants are transported downward by surface cracking or melting, they mix with the reduced compounds rising from the ocean. The result is a planet-wide redox system, balancing oxygen-rich and hydrogen-rich chemistry, the fundamental energy gradient that life requires. In this sense, radiation acts as a planetary catalyst, transforming stable molecules into reactive intermediates that feed deeper chemical cycles. The very process that sterilizes the surface may fertilize the ocean. Europa's reddish streaks, visible from space, are likely deposits of radiolytically processed organics, the chemical fingerprints of this cosmic interplay. On Enceladus, Saturn's weaker magnetosphere reduces surface radiation, allowing more pristine preservation of compounds. Its plumes thus serve as windows into relatively unaltered chemistry, while Europa's crust records the ongoing dialogue between destruction and creation. Water is more than a solvent. It is a reactant and a medium for transformation. Its polarity allows it to dissolve salts, mediate ion exchange, and stabilize complex molecules. In the high-pressure environments of subsurface oceans, water exhibits unique properties, forming clathrate hydrates, altering solubility, and enabling reactions impossible in surface conditions. At pressures exceeding 100 megapascals, as on Europa's ocean floor, carbon dioxide dissolves efficiently, facilitating the formation of carbonic acid and subsequent reactions leading to carbonates and organics. The combination of water, carbon, and energy thus forms a self-organizing chemical ecosystem, a set of reactions feeding and balancing each other over geologic time. Ammonia, often present in these environments, further enhances the chemistry. Acting as an antifreeze, it lowers the freezing point of water and contributes nitrogen to organic synthesis. The resulting ammonia-water mixture creates a flexible environment where both polar and non-polar molecules can coexist, crucial for forming membranes and protocellular structures. Laboratory experiments simulating Europa's ocean conditions have successfully produced amino acids, lipid-like compounds, and nucleotide precursors under hydrothermal and radiolytic influence. The frozen seas, it seems, have all the necessary ingredients to replay the origin of life on an extraterrestrial stage. Beyond Europa and Enceladus, other worlds contribute to the growing picture of cosmic organic chemistry. Titan, Saturn's largest moon, is a world drenched in hydrocarbons, methane rain, ethane lakes, and nitrogen haze. Its atmosphere is a chemical factory driven by solar ultraviolet light and energetic particles, producing tholins, complex organic solids that fall like snow to the surface. If mixed with subsurface water or ammonia, these tholins could dissolve and reorganize into biomolecular precursors. Titan's chemistry represents a parallel path to complexity. Organic first, aqueous later. Even distant Pluto shows signs of active organic synthesis. The New Horizons mission found bright red regions, rich in tholins, formed by photolysis of methane and nitrogen ice. Though colder than any ocean world, Pluto likely harbors a deep subsurface ocean, insulated by nitrogen and ammonia ices. If radiogenic heat maintains circulation, chemical reactions similar to those on Europa may proceed at a slower pace. Across these diverse environments, the message is clear. Organic chemistry is ubiquitous, not a rare terrestrial accident. The detection of complex organics in icy moons raises a profound question. Where does chemistry end and biology begin? Simple molecules like methane, carbon dioxide, and ammonia can arise abiotically, but the formation of large structured compounds, such as amino acids, lipids, or nucleobases, requires sustained energy gradients and catalytic environments. Cassini's detection of macromolecular organics in Enceladus's plumes hinted at polymerization processes occurring within its ocean. The diversity of compounds, aromatic, aliphatic, nitrogenous, suggests a prebiotic chemistry approaching biological complexity. Future missions aim to distinguish between abiotic and biotic origins. The Europa Clipper spacecraft, launching in the 2020s, carries the MASSPEX, mass spectrometer for planetary exploration, capable of identifying isotopic ratios, molecular chirality, and complex organic structures in minute detail. The Dragonfly mission to Titan will analyze surface materials for amino acids and potential biosignatures. If these missions find molecules with specific enantiomeric excess, a preference for left or right-handed forms, it would hint at biological selection, since life on Earth universally favors one chirality. In this way, chemistry becomes the language by which we search for life's signature. In the cold, high-pressure environments of ocean worlds, chemical reactions proceed far more slowly than on Earth's surface. Yet the timescales are immense. Billions of years of uninterrupted reaction, circulation, and renewal. Over such spans, even sluggish processes can accumulate complexity. Minerals within the seafloor may act as catalytic scaffolds, concentrating molecules and fostering polymerization. Repeated cycles of freezing and thawing, as the ice crust flexes under tides, can concentrate solutes and drive condensation reactions. The same mechanism proposed for early Earth's tidal pools, but transposed to an alien ocean beneath ice. Time and stability, not temperature alone, may be the decisive factors in the emergence of life. The study of organic chemistry in frozen seas forces a profound rethinking of what it means for a world to be alive. It shows that life is not an anomaly, but a continuum, an emergent property of matter under the right energy and composition. The oceans of Europa and Enceladus may be engaged in the slow rehearsal of biogenesis, a planetary-scale experiment playing out unseen. Whether or not it has yet crossed the threshold into metabolism and replication, the chemistry is undeniably alive with potential. These frozen oceans remind us that the universe is not inert, but pregnant with chemistry, and that biology is the natural extension of geochemistry. Every molecule ejected from Enceladus's plumes, every dark streak on Europa's ice, tells us that nature's most creative force, the drive to organize, operates wherever water and carbon meet. The cosmos, in its vast coldness, is quietly assembling the alphabet of life, one molecule at a time. For most of human history, life and sunlight were inseparable. The sun's light feeds plants, warms the oceans, and drives the atmospheric engines that sustain every ecosystem on Earth's surface. Yet in the late 20th century, a revelation shattered that ancient assumption. In 1977, scientists exploring the Galapagos Rift discovered hydrothermal vent communities thriving 2.5 kilometers beneath the Pacific, in perpetual darkness. Tube worms, crabs, and microbes lived in abundance. Not through photosynthesis, but chemosynthesis, drawing energy from the oxidation of hydrogen sulfide spewing from volcanic vents. It was life without sunlight, life fed by the chemistry of the Earth itself. That discovery forever expanded the boundaries of biology and gave astrobiologists a living model for what might exist beneath the icy crusts of worlds like Europa and Enceladus, If life can thrive in Earth's abyss, where sunlight has never reached, then perhaps it can thrive anywhere liquid water, chemistry, and energy coexist. The dark oceans of other moons may thus harbour biospheres built on chemical energy, sustained by planetary heat rather than stellar radiance. In the silence beneath the ice, there may exist entire ecosystems invisible to the universe, self-contained, eternal, and luminous, only in the language of metabolism. Photosynthesis converts sunlight into chemical energy, using pigments and light-absorbing molecules. Chemosynthesis, by contrast, relies on redox reactions, the transfer of electrons between molecules of differing energy states. On Earth, chemosynthetic microbes harness compounds like hydrogen sulfide, H2S, methane, CH4, or molecular hydrogen, H2, oxidizing them to derive energy and fix carbon dioxide into organic matter. These microbes form the base of ecosystems at hydrothermal vents, cold seeps, and subsurface aquifers. In ocean worlds, similar reactions could provide a foundation for life. The ingredients are already there: water, rock, and chemical disequilibrium. At the seafloor of Enceladus, or Europa, serpentinization reactions release hydrogen gas as water interacts with olivine-rich rocks. This hydrogen could react with dissolved carbon dioxide or oxidants delivered from the surface, forming methane and other organics, just as it does on Earth's vents. Microbial analogues of Earth's methanogens could exploit this energy gradient, converting chemical imbalance into living order. This form of life would not require sunlight, chlorophyll, or atmosphere. It would live entirely inward-facing, feeding on the heat and chemistry of its planet. Its energy source, internal rather than external, would persist as long as the moon's tides and radioactivity endure. Thus, even after a star dies, a subsurface ocean could continue nurturing life for billions of years. These biospheres would be cosmic refuges, surviving long after their suns fade. To envision a biosphere without sunlight, we must imagine not a barren abyss, but a layered ecosystem adapted to darkness. At its foundation lie chemolitho-autotrophic microbes, organisms that derive both energy and carbon from inorganic reactions. These primary producers form microbial mats on vent chimneys or sediments, analogous to Earth's vent bacteria. Above them, more complex organisms, if evolution had time, could evolve by consuming the microbes or their byproducts. Even without multicellular life, microbial communities alone could form intricate ecological webs. Sulfate reducers, methanogens, and methanotrophs could coexist, cycling carbon and sulfur through the ocean. Hydrogen, sulfide, and iron ions would act as the currency of metabolism, exchanged in endless loops. Organic detritus could sink and recycle, just as on Earth. If hydrothermal activity is widespread, convection could distribute nutrients throughout the ocean, maintaining global circulation and preventing stagnation. Over geological timescales, such an ecosystem could achieve stability, an ecological homeostasis existing entirely in darkness. Some models even suggest that bioluminescence could evolve, not as communication through light, but as a biochemical byproduct of oxidation. In an ocean isolated from the sky, flashes of blue or green might flicker from microbial colonies near thermal vents, not to be seen by eyes, but existing nonetheless as signatures of chemical vitality. A critical question for such dark biospheres is whether enough energy exists to sustain life on a global scale. On Earth, hydrothermal ecosystems make up a tiny fraction of total biomass, dwarfed by the energy flux of sunlight. Yet the comparison may be misleading. On Europa or Enceladus, there is no competition with photosynthesis, no forests or planktonic blooms drawing from external light. The biological demand scales with availability. If the energy from tidal and radiogenic heat drives continuous hydrothermal circulation. The total energy flux could support dense microbial populations across the ocean floor. Estimates suggest that Enceladus's ocean releases about 15 gigawatts of thermal power, enough to maintain hydrothermal systems comparable in total output to Earth's mid-ocean ridges. The chemical energy available from hydrogen and methane oxidation could, in principle, sustain 10 to the power of 12 to 10 to the power of 13 cells per cubic meter near vent zones, densities similar to terrestrial seafloor sediments. Europa, with its larger size and greater tidal stress, could harbor even richer environments. Life there might exist in stratified zones, concentrated around vent fields, crustal cracks, or oxidant-rich upwellings. Even in low-energy environments, microbial life can persist in slow metabolism. On Earth, deep biosphere microbes reproduce once every 1,000 years, yet still endure. In icy moons, similar ultra-slow life could thrive. Metabolism stretched across geological time, surviving on trickles of energy from radiolysis and hydrothermal reactions. Such organisms might remain dormant for millennia, awakening when fresh chemical gradients appear. Life, once begun, rarely stops. It merely waits. In an ocean cut off from sunlight, adaptation favors efficiency and cooperation. Life must recycle every element, every molecule. Extremophiles on Earth show the range of what is possible. Organisms thriving at 120 degrees Celsius, near vents. Others surviving at -20 degrees Celsius, in Antarctic brines. And microbes enduring crushing pressures at the ocean floor. On Europa and Enceladus, pressures could reach hundreds of atmospheres, but liquid, water, and energy exist, the two immutable prerequisites of biology. Metabolic strategies could mirror those on Earth's seafloor. Methanogens, consuming hydrogen and carbon dioxide to produce methane. Sulfate reducers, using hydrogen to reduce sulfate to sulfide. Iron oxidizers and reducers, cycling iron between its oxidation states. Nitrate or perchlorate users, if such compounds exist from surface influx. Together, these communities would weave a complex biogeochemical tapestry, life feeding on the flow of electrons between chemical species, maintaining the planet's internal ecology. An additional twist may come from the delivery of oxidants from the surface. On Europa, radiation produces oxygen and peroxide in the ice. As the crust cracks under tidal stress, these oxidants descend, meeting the reducing hydrothermal fluids below. The meeting of oxygen and hydrogen, two opposite extremes, releases vast chemical energy, enough to power not just microbes, but potentially macrobiology if evolution allowed it. The ice itself becomes part of the ecosystem, a reservoir of potential energy slowly released into the ocean. The evolution of life in such enclosed oceans would follow a path of isolation and specialization. Without sunlight, sensory evolution might favor chemical detection, heat gradients, or magnetoreception rather than vision. Without continents or atmosphere, speciation could be driven by geological niches, hydrothermal vents, crustal fissures, or mineral-rich oases. Genetic exchange could occur through microbial conjugation or viral agents, ensuring slow but steady diversification. Over billions of years, evolution might lead to symbiotic consortia, microbial communities forming stable metabolic partnerships, recycling each other's waste. The result would be a self-sustaining, closed-loop biosphere, reminiscent of ecosystems that thrive in Earth's deepest crust. Some researchers speculate that if complex multicellular life ever evolved there, it would likely resemble Earth's vent fauna, soft-bodied, slow-moving, and entirely chemo-autotrophic. Yet even without complexity, microbial life alone would constitute a planetary-scale living system, an unseen biosphere, ancient and enduring. If such biospheres exist, They redefine what it means for a planet to be alive. They show that life is not dependent on stars, but on processes deeper than light. That the heartbeat of biology is not the photon, but the gradient. The universe, in this view, is not a collection of barren worlds awaiting sunlight, but a vast subsurface biocosm, teeming with potential life hidden beneath ice and rock. The majority of habitable environments in the galaxy may therefore be invisible. Concealed oceans orbiting distant giants, each sustaining its own secret ecology. This realization carries a humbling implication. Humanity, born on a surface world lit by a star, may be the exception, not the rule. The typical habitat of life in the cosmos could be dark, pressurized, and eternal, where day and night have no meaning, and existence depends solely on chemistry and heat. Life's universality may thus lie not in resemblance to Earth, but in its adaptability, its ability to harness any source of energy, however faint, to preserve complexity against entropy. Earth itself offers compelling analogues. Beneath continents and oceans lies the deep biosphere, a microbial realm extending kilometers into rock and sediment. There, life survives on hydrogen from radiolysis of water, sulfate reduction, or reactions between minerals. Estimates suggest that up to 10 to the 17th power tons of biomass, half of Earth's total microbial life, exists in these dark depths. Many of these organisms have metabolic rates so slow they may live for tens of thousands of years before dividing. They prove that sunlight is not life's boundary, but merely one of its tools. The hydrothermal vent ecosystems discovered on Earth are the living proof that life needs only chemistry and water. Entire communities flourish in conditions almost identical to those hypothesized for Europa's seafloor. If evolution could construct such systems on Earth within mere hundreds of millions of years, then given billions of years, it could surely do the same beneath another moon's ice. As the biologist Lynn Margulis once said, "Life is everywhere. It cannot be stopped. It will grow wherever there is energy and order." If dark biospheres are common, why have we not found them? The answer lies in their concealment. Subsurface oceans do not reflect light, emit radio waves, or produce atmospheric biosignatures. They are sealed ecosystems, visible only through indirect evidence, geysers, spectral lines, or isotopic anomalies. Life on Europa or Enceladus might be thriving right now, yet remain completely undetectable from Earth. Their invisibility teaches a final, sobering truth. The cosmos may already be full of life, but most of it is hidden by its own environment. The universe might be whispering, not shouting. The forthcoming Europa Clipper and Dragonfly missions mark the first attempts to listen more closely. They will sample plumes, analyze chemistry, and test for biomarkers, the molecular echoes of metabolism. A single confirmed biosignature would prove that sunlight is not the monopoly of life. It would show that biology is a universal response to chemistry, not an accident of our star. In the end, the prospects for biospheres without sunlight remind us that life is not fragile. It is adaptive, persistent, and cosmic. On worlds of eternal night, tides replace days, chemistry replaces light, and heat replaces hope. Yet, life endures, feeding on imbalance and transforming the inorganic into the living. The dark oceans beneath Europa and Enceladus are not anomalies but natural outcomes of planetary evolution. Oceans that may hum softly with unseen metabolism. Oceans that will outlive the sun itself. The irony is profound. In the coldest corners of the solar system may lie the warmest truth of all, that life does not need light to shine. For centuries, humankind gazed at the stars and wondered if other worlds could harbor life. Now, for the first time in history, that question is no longer confined to imagination. It is a matter of engineering precision and flight paths. The 21st century marks the dawn of the great return to the outer solar system, not to marvel at distant worlds from afar, but to touch, taste, and analyze them for signs of biology. At the heart of this new age of exploration stand two bold emissaries, NASA's Europa Clipper and Dragonfly. One will orbit Jupiter and fly past a moon that may conceal a global ocean beneath a veil of ice. The other will take to the skies of Titan, exploring dunes and ancient riverbeds of methane. Together, they represent the most ambitious attempt yet to answer the oldest question in science: are we alone? Europa has long haunted the imagination of scientists. Beneath its fractured crust lies more water than all the Earth's oceans combined, sealed away in perpetual darkness and warmed by tidal heat. The Europa Clipper mission, set for launch in the mid-2020s, is designed to explore that ocean indirectly, to fly close, sense, and listen for the whispers of life beneath the ice. It is, in essence, a reconnaissance of a world that may already be alive. Europa Clipper will not orbit Europa directly. Jupiter's immense radiation belts would quickly disable its systems, but will instead orbit Jupiter in a highly elliptical path, performing nearly 50 flybys of Europa over 4 years. Each pass will skim as close as 25 kilometers above the surface, allowing the spacecraft to map, sample, and analyze the Moon in exquisite detail. Its trajectory is a delicate dance, timed to minimize exposure to radiation, while maximizing scientific yield. Each close encounter will peel back another layer of Europa's mystery. Scientific payload, instruments of discovery. Clipper carries one of the most advanced payloads ever assembled for planetary exploration. A suite of 9 primary instruments designed to interrogate the Moon from surface to core. EIS, Europa Imaging System, will capture high-resolution images of the terrain, revealing ridges, cracks, and chaos fields that hint at subsurface activity. REASON, radar for Europa assessment and sounding, ocean to near surface, will penetrate up to 30 kilometers of ice, searching for liquid layers and subsurface lakes, the echoes of the ocean. MASPEX, Mass Spectrometer for Planetary Exploration/Europa, will analyze the composition of Europa's tenuous atmosphere and potential plumes, detecting organic molecules, isotopes, and volatile gases. SUDA, Surface Dust Analyzer, will study dust particles ejected into space, identifying salts, minerals, and organics. Europa UVS, Ultraviolet Spectrograph, will look for ultraviolet emissions that betray active plumes or auroral phenomena. ICEMAG, Interior Characterization of Europa using Magnetometry, and PIMS, Plasma Instrument for Magnetic Sounding, will measure induced magnetic fields and plasma interactions, helping to determine the depth and salinity of the subsurface ocean. MISE, Mapping Imaging Spectrometer for Europa, will map surface composition, identifying hydrated minerals and potential biosignature deposits. ETHEMIS, Thermal Emission Imaging System, will detect warm regions that may indicate recent cryovolcanic activity. Together, these instruments will paint a comprehensive picture of Europa as a living system. Its geology, ocean chemistry, and potential habitability intertwined. Europa Clipper's overarching goal is to assess habitability, not direct detection of life. It will measure the key ingredients, water, chemistry, and energy, that define a habitable world. By analyzing the surface and atmosphere, scientists hope to determine whether oxidants from radiation reach the ocean, whether organics are present, and whether active vents or plumes connect the two. If plumes are confirmed, MASPEX and SUDA will analyze their composition directly. searching for complex organics, amino acids, or isotopic signatures indicative of biological processing. Even without direct detection, these measurements could provide strong circumstantial evidence that Europa's ocean possesses all the conditions necessary for life. Europa Clipper is thus the pathfinder, not the colonizer. The mission that will decide whether the next step should be a lander or a cryobot capable of melting through the ice. It represents the first deliberate attempt to map another ocean world in detail, to read the chemical language of a sea no sunlight has ever touched. Operating near Jupiter is an act of audacity. The radiation environment around Europa is 400 times stronger than Earth's Van Allen belts, capable of degrading electronics in hours. Clipper's systems must be shielded by thick aluminum vaults, and its trajectory carefully planned to minimize exposure. Power comes from large solar arrays spanning 30 meters, the most distant and powerful ever flown. Every subsystem has redundancy. Every observation window is a chance that cannot be wasted. It is, in the words of its engineers, a spacecraft built to survive the wrath of a god. If Europa Clipper is the patient scientist, Dragonfly is the explorer. A flying laboratory bound for the skies of Titan, Saturn's largest and strangest moon. Where Europa hides an ocean beneath ice, Titan cloaks one beneath haze. Its dense nitrogen atmosphere, thick orange clouds, and methane rivers make it the most Earth-like world in the solar system, yet utterly alien. With surface temperatures near -180 degrees Celsius and lakes of liquid hydrocarbons. Titan offers a window into chemistry that may predate life itself. Dragonfly's mission is to roam that world, sampling dunes, deltas, and ancient impact sites for the ingredients of life. Dragonfly is not a rover or a lander. It is a nuclear-powered drone, capable of flying across Titan's surface using 8 carbon fiber rotors. Titan's low gravity and dense atmosphere make flight remarkably efficient. A human-powered drone could theoretically fly there with ease. Dragonfly will exploit this advantage, traveling hundreds of kilometers between sites, a level of mobility unprecedented in planetary exploration. It will launch aboard a heavy-lift rocket in the late 2020s and arrive in the 2030s after a 7-year journey, landing in Titan's equatorial dune fields near Shangri-La. Once there, Dragonfly will begin a multi-year campaign of exploration. Its payload includes DOTRA-MS, Dragonfly Mass Spectrometer, to analyze organic molecules in surface materials, DOTRA-GNS, Gamma-ray and neutron spectrometer, to measure elemental composition and search for subsurface liquid reservoirs, DRA-GMET, meteorology and geophysics package, to study weather, seismic activity, and atmospheric dynamics, DragonCam, a panoramic camera system for high-resolution imaging of Titan's alien landscapes, samples acquisition system for drilling and ingesting material into analytical chambers. Dragonfly will fly to multiple targets, including organic-rich dunes, possible cryovolcanic flows, and the impact crater Selk, where liquid water and organics may once have mixed. Each site will test a different hypothesis about Titan's chemical evolution, from prebiotic synthesis to potential modern activity. Unlike Europa Clipper, Dragonfly will be able to directly sample and analyze surface material, reading Titan's chemical history layer by layer. Titan's significance extends beyond habitability. It is a time capsule of chemical evolution. Its atmosphere, dominated by nitrogen and methane, mirrors that of early Earth before oxygenation. Sunlight and charged particles drive photochemical reactions that produce a smog of complex organics, tholins, that settle onto the surface. When mixed with liquid water during impact heating or cryovolcanic upwelling, these organics could undergo further reactions toward amino acids or nucleobase precursors. Titan thus bridges the gap between chemistry and biology, showing how organic complexity can flourish even without life. Dragonfly will seek to trace that bridge, testing whether Titan's dunes hide molecules that resemble the early stages of life's alphabet. Europa Clipper and Dragonfly are not isolated ventures, but part of a coordinated program, NASA's Ocean Worlds Exploration Strategy. Following them are proposed missions like Enceladus Orbilander, which would orbit and then land to sample geyser material directly, and Trident, targeting Neptune's moon Triton, suspected of recent cryovolcanism. Together, these missions form a fleet of explorers sent to test the universality of life's chemistry across the outer solar system. This coordinated vision reflects a shift in planetary science. The old paradigm, follow the water, has evolved into follow the chemistry. Scientists now seek to understand how each ocean world expresses the same principles: energy flow, molecular synthesis, and environmental stability. Whether beneath ice or within haze, the goal is the same: to trace the continuity between chemistry and life, between planet and organism. These missions are not only scientific, they are symbolic. They mark humanity's return to exploration on an epic scale, journeys measured in decades and billions of kilometers. In the tradition of Voyager and Cassini, Clipper and Dragonfly carry more than instruments. They carry curiosity, courage, and continuity, the human desire to know. The images they send back will not merely inform science, they will reshape philosophy. If we find organics or isotopic hints of metabolism, we will know that life is not a miracle, but a natural consequence of chemistry. If we find nothing, we will still have mapped the boundaries of possibility, an equally profound achievement. And perhaps, as Dragonfly hovers over Titan's dunes and Europa Clipper dives through a plume of vapor above the ice, humanity will glimpse itself in reflection. A species still learning that exploration is the essence of existence. The search for life on ocean worlds is no longer a dream. It is a technological trajectory already set in motion. By the mid-2030s, we will have tasted the breath of Europa's ocean and walked the surface of Titan's methane sands. Each mission will bring us closer to the moment when data becomes discovery, and discovery becomes understanding. Whether life exists beneath those frozen shells or not, these explorations will reveal something deeper: that the cosmos is alive with process, rich in chemistry and full of worlds waiting to be known. The 21st century will be remembered as the age when humanity opened the oceans of other worlds, and perhaps, in doing so, found a mirror of its own origins. Mars, the lost oasis. Long before human machines touched its surface, Mars was already whispering to us, a faint red spark in the night sky that stirred ancient imaginations. To the Babylonians it was Nergal, god of fire and war; to the Romans, a planet named for blood. Yet, modern science has uncovered a very different story beneath that crimson hue. A tale not of fire, but of water. For billions of years, Mars has carried the scars of flowing rivers, evaporating seas, and chemical traces of a wetter, more hospitable past. The wet Mars hypothesis has reshaped planetary science, revealing a world that once might have been alive. When the first spacecraft approached Mars in the 1960s, scientists expected to see canals and oceans. Instead, Mariner 4 in 1965 returned images of a cratered wasteland, barren, ancient, and seemingly dead. Yet appearances were deceiving. Later missions, Mariner 9, Viking, and the orbiters that followed, revealed networks of dry valleys and channels, vast outflow plains, and deltas shaped unmistakably by liquid water. From orbit, these ancient riverbeds snake across the highlands, converging in basins that may once have held lakes or shallow seas. Their geometry, dendritic, branching and meandering, mirrors terrestrial river systems, sculpted by rainfall and erosion. Mars, it seems, was once warm enough for liquid water to flow across its surface. The evidence deepened with Mariner 9's arrival in 1971. For the first time, an entire planet came into view, its atmosphere clearing from global dust storms to reveal canyons, volcanoes, and channels hundreds of kilometers long. Among the most striking were the outflow channels of Chrysi Planitia and Casei Valles, colossal flood scars suggesting the release of enormous volumes of water from underground aquifers or melting ice. Elsewhere, the valley networks of the southern highlands indicated sustained surface runoff, possibly from precipitation. These features implied not transient floods, but a long-lived hydrological cycle. Rainfall, rivers, lakes, and perhaps even oceans. The northern hemisphere of Mars, lower and smoother than the south, may once have been the floor of a vast ocean, covering 1/3 of the planet. This hypothesis, first proposed in the 1990s, gained support from shoreline-like features observed in orbital topography and sedimentary deposits in regions such as Arabia Terra and Utopia Planitia. Although later research revealed complications, tectonic tilting, erosion, and the difficulty of confirming true coastlines, multiple lines of evidence suggest that standing bodies of water did exist. The northern lowlands likely hosted intermittent seas or ice-covered lakes during Mars's warmer epochs. But perhaps the most compelling evidence for a wet past lies not in the planet's topography, but in its mineralogy. The Martian surface preserves a record of chemical weathering frozen in time. Orbital spectrometers, such as those aboard Mars Express and the Mars Reconnaissance Orbiter, have detected clays, phyllosilicates, sulfates, and hydrated minerals, all products of long-term interaction between rock and liquid water. These minerals act as planetary fossils, encoding the chemistry of vanished environments. In some regions, like Morth Vallis and Nili Fosse, layers of clay minerals suggest ancient lakes or groundwater systems that persisted for millions of years. Clays are especially significant because they can trap and preserve organic molecules, shielding them from radiation, a potential ark for the memory of life. The story written in Martian minerals divides its history into distinct climatic epochs. During the Noachian period, approximately 4.1 to 3.7 billion years ago, Mars was warm and wet enough for widespread surface water. Rain or snowmelt carved valleys, and basaltic crust interacted chemically with water to form clays. As the planet cooled, the Hesperian period, approximately 3.7 to 3.0 billion years ago, brought volcanic outflows and transient floods. A world of episodic water rather than global seas. Finally, the Amazonian period, from 3 billion years ago to the present, saw Mars become cold, dry, and oxidized, with water retreating to polar ice caps and underground reserves. The transformation was slow but relentless, an atmospheric unraveling that turned a blue world red. Why Mars lost its water remains one of planetary science's great mysteries. Early Mars likely possessed a thicker atmosphere rich in carbon dioxide, creating a greenhouse strong enough to sustain liquid water. But as the planet's magnetic field faded, perhaps due to the cooling of its core, the solar wind began to strip away atmospheric gases. Over hundreds of millions of years, Mars's air thinned, pressure dropped, and surface water boiled or froze. What remained was locked as ice in the soil and polar caps, or as hydrated minerals within the crust. NASA's MAVEN mission has since confirmed that this atmospheric escape continues today, with hydrogen and oxygen still leaking into space. Mars's lost air is a slow exhalation into the void. Despite this desiccation, the fingerprints of ancient water persist everywhere. The Jezero crater, where NASA's Perseverance rover now roams, preserves one of the most striking examples. A fossilized river delta, complete with layered sediments, channels, and fan-shaped deposits. These features could only have formed in a long-standing lake, fed by a river system active for thousands of years. Clay and carbonate minerals in Jezerose rocks further confirm a history of aqueous alteration. Such environments, deltas and lake beds rich in sedimentary layers, are prime targets for the search for biosignatures, for they preserve fine-grained records of habitability. Elsewhere, Curiosity's exploration of Gale Crater revealed mudstones, cross-bedded sandstones, and nodules of hematite, all signs of a once habitable environment. The rover's instruments detected clay minerals and evidence of neutral pH water, conditions suitable for microbial life. Ancient stream beds in the crater floor record gentle, persistent flows rather than catastrophic floods. These discoveries, combined with isotopic measurements of carbon and hydrogen, suggest that Mars once possessed a sustained hydrological cycle: evaporation, condensation, and precipitation, albeit one that eventually collapsed as the atmosphere thinned. Even today, Mars retains traces of this lost water. Polar caps of water ice and dry ice wax and wane with the seasons. Radar soundings reveal subsurface ice sheets extending into mid-latitudes, and occasional landslides, and gullies hint at transient flows of briny water. In 2018, radar data from the Mars Express orbiter suggested the presence of a subglacial lake beneath the southern polar ice cap, though later studies cast doubt on its permanence, suggesting it may be slushy or intermittent. Still, these observations confirm that Mars is not entirely dry, but a world in which water continues to cycle, frozen, hidden, and fleeting. The chemical story complements the geological one. Sulfate deposits indicate evaporation of acidic waters. Carbonates suggest more neutral chemistry. Together, they portray a planet whose surface environments evolved chemically as it lost its atmosphere. Early neutral and alkaline waters favored clay formation, while later acidic brines left behind sulfates and salts. This chemical stratigraphy allows scientists to read Mars's climatic history as one might read tree rings, a chronology of environmental change written in stone. The implications of the wet Mars hypothesis are profound. Where there was water, there may have been life. Microbial ecosystems could have thrived in lakes, rivers, or hydrothermal springs, shielded from ultraviolet radiation by water and sediments. The same processes that fostered life on early Earth, chemical gradients, mineral catalysis, and stable liquid water, existed on Mars as well. Whether life ever arose there remains unknown, but the planet's ancient geology shows that it once met nearly all the criteria of habitability. The great question is not whether Mars could have supported life, but whether it did, and if so, whether remnants of that biology still lie buried beneath its dust. In the end, the image of a wet Mars transforms our view of the solar system. It reveals a planet that was once alive with rivers, storms, and perhaps microbes, a twin of Earth that diverged only through fate and physics. The dry valleys and oxidized sands we see today are not marks of death, but fossils of vitality, the remains of a planet that once flowed. Mars may be barren now, but its memory is aqueous. Its rocks remember rain. The exploration of Mars is one of humanity's most enduring scientific sagas, a story spanning half a century of ambition, ingenuity, and discovery. From the cautious optimism of the 1970s to the precision robotics of the 21st century, our machines have transformed the red planet from an object of myth into a world of data, texture, and chemistry. Yet despite decades of exploration, one question continues to haunt every mission. Is there, or was there ever, life on Mars? The answer remains elusive, but the search has revealed a planet far more complex and far more Earth-like than we ever imagined. In the mid-1970s, NASA's Viking 1 and Viking 2 missions became the first spacecraft to successfully land and operate on the Martian surface. Each comprised an orbiter and a lander, working in tandem to map, photograph and sample the planet. Their descent onto the plains of Chryse Planitia and Utopia Planitia marked humanity's first direct encounter with another planet's soil. The Vikings were equipped with instruments designed specifically to detect signs of life. A bold move for a time when Mars's true environment was still largely unknown. The Viking biology package consisted of 3 experiments: the labeled release, LR, gas exchange, GEX, and pyrolytic release, PR, tests. These were designed to detect metabolic activity in Martian soil by adding nutrients and monitoring for gas emissions or organic synthesis. The LR experiment, in particular, produced tantalizing results. After the nutrient solution was added, the soil emitted small bursts of gas, consistent with biological metabolism. However, subsequent tests, including thermal sterilization and the absence of detectable organic molecules, cast doubt on the interpretation. Many scientists concluded that the reactions were chemical rather than biological, caused by reactive oxidants in the soil. Yet others, including experiment designer Gilbert Levin, continued to argue that Viking may have indeed found life, a debate that still flickers decades later. The gas chromatograph mass spectrometer, GCMS, aboard Viking, designed to identify organic molecules, found none. This was a crushing blow to hopes of detecting life, but later missions would reveal a twist. The instrument's heating process likely destroyed organics by reacting with perchlorates, highly oxidizing salts later discovered on Mars. The Vikings, in their technological innocence, may have inadvertently erased the evidence they sought to preserve. Nonetheless, their legacy endures. The data they returned, on atmospheric composition, surface chemistry and weather, formed the foundation of all subsequent Mars science. After Viking, Mars exploration entered a period of pause and reflection. The apparent sterility of its surface cooled public enthusiasm, and missions shifted toward orbital reconnaissance. The 1990s marked the beginning of a new era with Mars Global Surveyor, 1997, and Mars Odyssey, 2001, which mapped the planet in unprecedented detail. Mars Global Surveyor's laser altimeter revealed the planet's global topography, confirming the dichotomy between the cratered southern highlands and the smooth northern plains. Its magnetometer discovered remnant crustal magnetism, evidence that Mars once had a global magnetic field, and by extension, a once active core capable of shielding an atmosphere. Mars Odyssey, using a gamma-ray spectrometer, detected vast quantities of subsurface hydrogen, interpreted as water ice, at high latitudes. Mars, it turned out, was not as desiccated as it seemed. In 2004, NASA's twin rovers Spirit and Opportunity landed on opposite sides of Mars. Their missions were simple in concept, but revolutionary in execution, to follow the evidence of water. Each rover carried a suite of cameras, spectrometers, and drilling tools, designed to read the planet's geological record like a book of stone. Spirit, landing in Gusev crater, found volcanic plains rather than the expected lake sediments. Yet as it climbed the Columbia Hills, it discovered layered rocks containing goethite and sulfates, minerals that form only in the presence of water. Its findings revealed that even in apparently dry regions, Mars's subsurface had once been altered by fluids. Opportunity, meanwhile, achieved one of the most remarkable success stories in robotic exploration. Touching down in Meridiani Planum, it immediately found hematite blueberries, spherical concretions formed in liquid water. Later, it uncovered cross-bedded sandstones and sulfate-rich evaporates, confirming that acidic groundwater had once flowed through the rocks. What was expected to be a 90-day mission lasted nearly 15 years, covering 45 kilometers of Martian terrain. Opportunity's images of rippled dunes and ancient shorelines transformed scientific consensus. Mars had once hosted standing water, albeit acidic and transient. The red planet had a hydrological history as complex as Earth's deserts and deltas. While the rovers explored the equatorial regions, NASA's Phoenix lander ventured to the Arctic plains. In 2008, its robotic arm dug into the soil and exposed bright patches that sublimated in days. Water ice, directly confirmed by its onboard chemical analysis. Phoenix also discovered perchlorate salts, compounds capable of lowering water's freezing point and sustaining brines in sub-zero conditions. These findings revealed that Mars's surface and atmosphere were chemically active, and that water, though frozen, remained part of the planet's ongoing processes. The detection of perchlorates later explained why Viking's experiments had failed to identify organics. The same oxidants that preserved Mars's redness also destroyed fragile carbon compounds upon heating. In 2012, the Curiosity rover descended dramatically into Gale Crater, an ancient impact basin chosen for its layered sedimentary mound, Mount Sharp. This mission represented a new phase. No longer just a search for water, but a search for habitability. Curiosity's advanced laboratory suite, including the SAM, sample analysis at Mars, and Scheemann instruments, allowed direct analysis of rocks, soils, and gases. Early in its mission, Curiosity drilled into fine-grained mudstones and detected clay minerals, sulfur and nitrogen, all key ingredients for life. The sediments revealed neutral pH water conditions and evidence of ancient lake beds that persisted for thousands, perhaps millions of years. Crucially, Curiosity detected organic molecules, simple carbon-based compounds such as chlorobenzene and theophanes. While not proof of biology, these organics proved that carbon chemistry survives on Mars, despite harsh surface conditions. Later, Curiosity identified seasonal methane variations in the atmosphere, periodic increases and decreases suggestive of localized release. The source remains unknown, but methane's transient presence hints at either ongoing geochemical processes or, tantalizingly, subsurface microbial activity. In the layered mudstones of Gale Crater, Mars revealed itself not as a static corpse, but as a geologically and chemically active world. While rovers explored the surface, NASA's InSight mission turned its instruments inward, studying Mars's internal structure. Using a seismometer and heat probe, InSight recorded Mars quakes, revealing a planet still trembling with geological vitality. The data showed a surprisingly thin crust and a liquid metallic core, confirming that Mars remains thermally dynamic, albeit less active than Earth. Such internal heat could sustain subsurface liquid water and, potentially, life in localized environments. Even as the surface froze, the planet's heart continued to beat. The most ambitious mission yet, Perseverance landed in 2021 in Jezero Crater, chosen precisely because it once hosted a river delta, a perfect environment for the preservation of biosignatures. Equipped with advanced instruments and the ability to collect and cache rock samples for future return to Earth, Perseverance represents the culmination of decades of technological evolution. Its onboard systems, including PIXL, an X-ray spectrometer, Sherlock, a Raman spectrometer with fluorescence detection, and the MOXIE experiment, are designed to study mineralogy, search for organic molecules, and even test the production of oxygen from carbon dioxide for future human missions. In its first years, Perseverance confirmed that Jezero's rocks formed in sustained watery conditions, with fine-grained sediments ideal for preserving potential microfossils. It has also discovered complex organic carbon in multiple rock layers, strengthening the case that Mars once possessed the chemistry necessary for life. The mission's companion, the Ingenuity helicopter, achieved the first powered flight on another planet, proving that Mars's thin air could still carry the weight of human invention. Together, perseverance and ingenuity mark a new era. Not just observing Mars, but experimenting with it, treating it as an active, evolving world rather than a relic. Across 50 years of exploration, Mars has evolved from a mythic desert to a dynamic world with weather, chemistry, and memory. Viking showed us the surface. The orbiters mapped its scars. The rovers touched its ancient lakes. And Perseverance now reads its sediments like the pages of a planetary autobiography. The cumulative results have rewritten the narrative. Mars was once habitable, remains geologically active, and continues to exchange gases with its atmosphere. It is a planet not dead, but dormant, a world in intermission. The next great leap will be the Mars Sample Return mission, planned for the 2030s, which will bring Perseverance's cached rocks to Earth for laboratory analysis. Within those tiny cores may lie the first direct evidence of extraterrestrial life: fossilized cells, organic isotopes, or chemical patterns of metabolism. If confirmed, it will mark the moment when Mars ceases to be a mirror of Earth's past and becomes its biological sibling. In the end, the robotic emissaries of humanity have done more than explore another planet. They have held up a mirror to our own origins. Through their eyes, we have seen rivers dry, atmospheres vanish, and habitability fade. Mars teaches us that worlds are fragile, that climate and magnetism, chemistry and chance can decide a planet's fate. Yet it also reminds us of endurance. Though stripped and scarred, Mars still bears the imprint of its living potential. The red dust conceals not death, but the possibility that life never truly left, that beneath its frozen plains, the story continues. Of all the discoveries on Mars, none has provoked as much fascination and controversy as the detection of organic molecules and methane, the chemical fingerprints of potential biology. Each molecule by itself is ambiguous, explainable by both life and chemistry. Yet together they form a riddle that has haunted planetary science for decades. Methane flickers in Mars's atmosphere like a heartbeat, appearing and vanishing without clear cause. Organics hide in rocks and dust, ancient yet persistent. The planet whispers chemistry that resembles life, but never quite declares it. In these spectral traces lies perhaps the greatest scientific mystery of our time. Is Mars alive, or merely echoing the processes that once were? The search for organics on Mars began in earnest with the Viking landers in 1976. Their gas chromatograph mass spectrometer, GCMS, was designed to detect organic compounds in Martian soil. To universal surprise, it found none. Not even the simplest carbon chains expected from meteoritic infall. The result seemed definitive. Mars was chemically sterile. Yet even then, there were inconsistencies. The Viking biology experiments, which tested for metabolic gas release, produced puzzling positive signals, later dismissed as chemical reactions with oxidants in the soil. Only decades later would scientists uncover the missing piece: the discovery of perchlorates, reactive salts that, when heated during Viking's analysis, destroyed any organics present. The absence of detection, it turned out, was not absence of substance, but a methodological mirage. The Viking landers may have burned the very evidence they sought. Modern instruments, more sensitive and aware of these chemical pitfalls, have since rewritten Viking's verdict. In 2004, the Mars Express orbiter detected methane in the atmosphere using its planetary Fourier spectrometer. A startling result. Methane is inherently unstable under Martian conditions. Ultraviolet light and chemical reactions with oxidants should destroy it within centuries. Its presence, therefore, implies an active source, either geological or biological. Yet subsequent measurements revealed a mystery. Methane levels fluctuate dramatically, appearing in localized plumes and then disappearing within months, far faster than known destruction processes can explain. Follow-up observations from Earth-based telescopes, including the Keck Observatory and NASA's Infrared Telescope Facility, confirmed intermittent methane detections. Some plumes measured up to 60 parts per billion by volume, ppBeV, concentrated over specific regions like Arabia Terra and Syrtis Major. The pattern suggested localized release, not global emission. For a time, Mars seemed to breathe, exhaling bursts of methane, then falling silent. Curiosity's ground truth. When Curiosity landed in Gale Crater in 2012, it carried the sample analysis at Mars' SAM suite, a miniature laboratory capable of detecting organics and gases directly from rock samples. In 2014, SAM reported the first definitive detection of organic molecules in Martian sediments. These included chlorobenzene and simple thiophenies, carbon compounds that, while not biological themselves, require preservation within a stable environment. The mudstones of Gale Crater had shielded these molecules from ultraviolet destruction for billions of years, preserving them like chemical fossils. Later analyses revealed even more complex organics, including aromatic hydrocarbons and sulfur-bearing compounds, precisely the kinds that on Earth can arise from biological or geochemical processes alike. But perhaps Curiosity's most tantalizing finding came not from rocks, but from the air. Its tunable laser spectrometer detected seasonal methane variations, rising and falling with the Martian year. Concentrations peaked around 0.7 parts per billion by volume during the southern summer and dropped in winter. A periodicity suggestive of environmental control. Even more surprising were brief spikes up to 7 parts per billion by volume, recorded over just a few days. These transient bursts hinted at active release from subsurface reservoirs. Something, somewhere on Mars, was emitting methane, and something else was destroying it far faster than expected. The transient nature of methane on Mars has defied simple explanation. On Earth, about 90% of methane comes from biological sources, microbes, wetlands, and decay, while the rest arises from geological processes such as serpentinization, in which water reacts with olivine-rich rocks to release hydrogen that reduces carbon compounds. Both pathways could, in principle, occur on Mars. The planet's crust contains abundant olivine, and evidence of past hydrothermal activity is widespread. If liquid water once circulated through the crust, it could have generated methane abiotically. Alternatively, ancient microbial ecosystems may have produced methane long ago, now trapped in permafrost as clathrates, and released intermittently through fissures as the ground warms or shifts. Yet none of these hypotheses fully explains the rapid disappearance of methane after release. Known photochemical processes cannot destroy it so quickly. One possibility is that surface oxidants, such as perchlorates or dust-bound radicals, catalyze its breakdown. Another is that electrostatic discharges during dust storms oxidize methane locally. Still another proposes that micro-absorbed methane reacts within regolith grains, effectively sequestering it. Whatever the mechanism, Mars appears to possess an unrecognized atmospheric sink, a mystery chemical metabolism of the planet itself. The European Space Agency's Trace Gas Orbiter, TGO, launched in 2016, was designed to resolve this enigma with unprecedented sensitivity. To the astonishment of scientists, it detected no methane above a few parts per trillion, 3 orders of magnitude lower than Curiosity's readings. The contradiction sparked intense debate. Could local microenvironments produce methane that dissipates before reaching higher altitudes? Could diurnal cycles, surface chemistry, or instrument differences explain the discrepancy? The answer remains unclear, but the consensus is emerging that Mars's methane is episodic, localized, and dynamically recycled, perhaps from shallow subsurface pockets that vent sporadically and oxidize quickly. Beyond methane, Mars holds a deeper record of organic chemistry locked within its rocks. Curiosity's analyses of the Gale crater mudstones revealed that organic preservation depends on both mineral protection and environmental stability. Iron and sulfur-bearing minerals, particularly pyrite and jarosite, appear to have encapsulated organics from degradation. These compounds, when heated in SAM's ovens, released fragments of aromatic hydrocarbons and thiophenies, chemical fingerprints of complex carbon frameworks. Isotopic measurements of carbon revealed subtle enrichment patterns that, while not conclusively biological, are intriguingly consistent with ancient fractionation by life or photochemistry. Meanwhile, the Perseverance rover in Jezero crater has strengthened this picture. Its Sherlock instrument, scanning habitable environments with Raman and luminescence for organics and chemicals, has identified multiple classes of organic carbon distributed within sedimentary rocks. These organics co-occur with minerals that form in water, suggesting that early Mars hosted not only habitable environments, but also the building blocks for prebiotic chemistry. In some samples, the organics appear concentrated along mineral fractures, possible evidence of migration through groundwater. If true, this implies that Mars's subsurface was chemically active long after its surface dried, perhaps sustaining life-friendly niches for hundreds of millions of years. The mystery of Martian organics extends beyond the planet itself. In 1996, scientists studying the Allen Hills 84001 meteorite, a 4.1 billion-year-old rock ejected from Mars and recovered in Antarctica, announced potential evidence of fossilized microbes, tiny worm-like structures embedded in carbonate globules. The claim ignited both excitement and skepticism. Later analyses showed that similar shapes could form through abiotic processes, and the supposed magnetite crystals could be explained by thermal alteration. Yet the meteorite undeniably contains organic molecules, as well as isotopic ratios hinting at low-temperature aqueous processes. Whether biological or not, ALH 84001 demonstrates that Mars once supported complex organic chemistry, the raw material for life. Subsequent Martian meteorites, including Nakla, Shergotite, and Tisint, have also revealed traces of organics and water alteration. Some contain amino acid-like compounds and evidence of hydrothermal activity. Collectively, these meteorites serve as time capsules of early Martian environments, linking the planet's geologic past with its chemical potential. They remind us that the boundary between organic chemistry and biology may be thinner than we assume, and that the distinction between life and pre-life may hinge on context, not composition. The coexistence of organics, oxidants, and transient methane makes Mars a paradox. The same chemistry that preserves carbon compounds also destroys them. The planet's surface is both a cemetery and a laboratory, a place where organics endure in shadowed rocks, but perish in sunlight. The atmosphere, thin yet reactive, cycles trace gases faster than models can explain. The crust, riddled with fractures and ice, stores ancient memories of habitability while exhaling cryptic plumes that vanish as if swallowed by the wind. In every sense, Mars is chemically alive, even if biologically uncertain. One interpretation suggests that what we see is the ghost of a biosphere, a remnant geochemical metabolism, still flickering in the subsurface. Methane and organics may be the dying embers of ancient microbial processes, sustained intermittently by geothermal warmth or briny pockets. Alternatively, they may be purely geological, arising from reactions between rock and water in a planet that still breathes through its crust. Either way, the result is the same. Mars is not inert. It is a world with ongoing exchange, a place where matter still moves, reacts, and evolves. The mystery of Martian methane transcends chemistry. It redefines planetary vitality. It shows that even a world long considered dead can remain dynamic on chemical and perhaps biological timescales. Mars may have lost its seas and atmosphere, but not its potential. The discovery of organics and transient methane teaches us that habitability is not a binary condition, but a spectrum, one that can shift, retreat, and reawaken. A planet need not teem with forests to be alive. It need only host the chemical rhythm of exchange. For astrobiology, these findings mark a turning point. The search for life is no longer about fossils or green patches, but about chemical persistence. The slow dialogue between rock and gas, molecule and light. Methane, fleeting though it is, proves that Mars is still speaking. And organics, buried though they are, prove that Mars remembers. Somewhere beneath its frozen dust, in the fractures of Jazero's delta or the pores of ancient clays, the story continues. A conversation between past and present, between chemistry and life. Whether we call it biology or geochemistry, Mars is a planet still breathing softly in the dark. If life still exists on Mars, it is almost certainly hidden, buried beneath the irradiated dust and freezing winds, far from the deadly glare of the sun. The planet's surface today is one of the most hostile environments in the solar system. Temperatures plunge below -100 degrees Celsius. Atmospheric pressure hovers near the triple point of water, and ultraviolet radiation bathes the land unfiltered. Yet below that desolation may lie refugia, pockets of warmth, water, and protection. The planet's last sanctuaries of habitability. These underground havens, coupled with terrestrial analogues that mimic Martian conditions, form the frontiers of modern astrobiology. To understand whether Mars still harbors life, we must first learn how life hides. Mars's surface, though geologically beautiful, is chemically lethal. Its regolith is rich in perchlorates and superoxides, reactive compounds that destroy organic molecules and render the soil sterile. Cosmic radiation, unshielded by a dense atmosphere or magnetic field, penetrates to depths of several meters, breaking chemical bonds and sterilizing the upper crust. For any organism, survival on the surface would be nearly impossible over geologic timescales. Yet, just a few meters below, conditions change dramatically. The soil becomes shielded from radiation, temperatures stabilize, and traces of ancient water may persist as ice, brine, or hydrated minerals. These hidden environments, where geology, chemistry, and potential biology converge, define the Martian subsurface refugia hypothesis. Evidence from orbiters and landers supports this view. Radar soundings from the Mars Reconnaissance Orbiter, MRO, have revealed massive deposits of subsurface ice, some extending into equatorial latitudes. In mid-latitude regions, features known as Labatt debris aprons appear to contain buried glaciers beneath thin mantles of dust. Impact craters occasionally expose bright layers of ice, only to see them sublimate within days, indicating that frozen water lies just beneath the surface. Meanwhile, recurring slope lineae, dark streaks that appear seasonally on crater walls, suggest transient flows of briny liquid water, although their precise nature remains debated. The message is consistent. Mars is dry only on the surface. Below, it still holds the memory of water. The thermal and pressure gradients of Mars's crust create potential zones where liquid water could exist stably. Models suggest that at depths of 1 to 3 kilometers, temperatures may rise above the freezing point due to geothermal heat, while overlying pressure prevents evaporation. In these conditions, subsurface aquifers or brine pockets could persist for billions of years. Perchlorate and sulfate salts lower the freezing point of water to -70 degrees Celsius, or lower, allowing brines to remain liquid even in cold environments. These chemical antifreezes could sustain cryobrines, salt-saturated solutions that serve as both solvent and nutrient source for microbes. On Earth, analogous systems thrive deep underground. Microbes have been found living kilometers beneath the continents and oceanic crust, sustained entirely by geochemical reactions. In South African gold mines, Desulforudis audax viator lives off hydrogen produced by radiolysis of water, a process identical to what could occur in Martian rock. Similarly, at hydrothermal systems beneath the ocean floor, chemolithautomorphs derive energy from hydrogen, sulfur, and iron oxidation, independent of sunlight. These deep biospheres prove that life does not require light, only energy gradients and liquid water. If Mars possesses even trace geothermal activity, its subsurface could host parallel ecosystems, dormant or active. Another class of potential refugia lies within lava tubes and cave systems, remnants of Mars's volcanic past. Orbiters have photographed dozens of pit craters, circular holes leading into darkness, some large enough to swallow a skyscraper. These features, found near volcanoes like Arsia Mons and Pavonis Mons, likely open into vast underground chambers formed when flowing lava cooled and drained. Inside, temperatures are stable, radiation is minimal, and humidity could be higher than the desiccated surface. On Earth, lava tubes on Hawaii and the Canary Islands harbor rich microbial mats that feed on mineral surfaces and trapped moisture. Such environments could serve as ideal analogues for Martian caves, natural bunkers for biology. Recent studies using high-resolution cameras and thermal imaging show that Martian caves may maintain internal temperatures around -20 degrees Celsius, warmer than the ambient surface average. Seasonal frost may deposit water vapor inside, and dust from volcanic glass provides reactive surfaces for chemistry. For future human missions, these caves offer potential habitats. For astrobiology, they may be the best hope for finding extant life. If microbial ecosystems persist on Mars today, they likely dwell in the transition zones between ice, rock, and air, interfaces rich in gradients of energy and moisture. Because direct access to the Martian subsurface remains limited, scientists turn to Earth analogues, extreme environments that replicate key Martian conditions. In Antarctica's McMurdo Dry Valleys, ice-free deserts with near-zero humidity host endolithic microbes living within translucent rock. These organisms survive on trace water from melting ice and protect themselves from ultraviolet radiation by burrowing just millimeters below the surface. Similar communities thrive inside halite salt crystals in the Atacama Desert of Chile, one of the driest places on Earth. There, microorganisms extract moisture directly from the atmosphere and use photosynthetic pigments to capture faint light, strategies that could work on Mars under thin sunlight and high salinity. Another analogue lies in the Rio Tinto of Spain, an acidic river system sustained by iron-oxidizing microbes that live in pH levels below 2. Their metabolism produces red iron oxides nearly identical to those covering Mars's surface. The Rio Tinto microbes demonstrate that life can persist in acidic, metal-rich, and oxidizing environments, precisely the chemistry detected by rovers in places like Meridiani Planum and Gale Crater. Likewise, the geothermal springs of Iceland and Yellowstone provide models for early Mars's hydrothermal systems, where heat and water interact through basaltic rock, producing conditions ripe for chemosynthetic life. Even in the present Martian cold, microbial life could survive in states of cryptobiosis, dormancy at the edge of metabolism. On Earth, permafrost samples from Siberia and Antarctica have yielded viable microbes tens of thousands of years old. Spores of bacillus species, preserved in salt crystals and amber, have survived for millions of years. In Mars's permafrost, shielded from radiation and oxidants, spores or dormant cells could endure for eons, reawakening whenever local conditions briefly thaw. Periodic geothermal heating, impacts, or even obliquity-driven climate cycles might trigger episodic melting, allowing metabolism to resume before freezing again. Life on Mars, if it exists, may follow a pulse of awakening, cycles of activity separated by long dormancy, synchronized with the planet's climate rhythms. Beyond biology, the Martian crust itself may serve as a geochemical engine. When basalt interacts with water, it produces hydrogen gas through serpentinization, a key energy source for microbes. Radiolysis, driven by uranium, thorium, and potassium decay, splits water into oxidants and reductants, sustaining redox gradients that could feed chemolithoautotrophs. Minerals such as magnetite and sulfides provide catalytic surfaces for organic synthesis. Even in the absence of biology, these reactions generate the precursors of life: methane, formaldehyde, and other reduced carbon compounds. Thus, Mars's subsurface could be simultaneously a habitat and a laboratory, testing whether prebiotic chemistry can persist independently of life. Searching for signs. The instruments and the clues. Modern missions are now tuned to probe these refugia indirectly. The ExoMars Rosalind Franklin rover, scheduled for launch in the late 2020s, carries a drill capable of reaching 2 meters below the surface, far deeper than any previous rover. Its MOMA, Mars Organic Molecule Analyzer, instrument will search for complex organics preserved beneath the sterilizing radiation layer. NASA's planned Mars sample return will eventually bring back cores from sedimentary rocks that may contain mineralogical or isotopic hints of subsurface exchange. Orbital instruments such as SHARAD and MARSIS continue to map underground ice, while the Trace Gas Orbiter tracks atmospheric methane plumes to locate potential venting sites. Together, these missions outline a vision of Mars as a layered world. Its surface barren, but its depths chemically alive. The search for subsurface life is therefore not just a matter of detection, but of interpretation, recognizing patterns of chemistry, isotopic ratios, and mineral assemblages that indicate continuity of habitability. Exploring Mars's subsurface raises profound ethical questions. If refugia exist, we must ensure they remain uncontaminated. Robotic landers and future human missions risk delivering terrestrial microbes that could colonize or alter native environments, confusing future detections. Planetary protection protocols aim to prevent forward contamination, treating Mars not merely as a scientific object, but as a biological preserve. To probe its refugia is to enter a sacred domain, the possible cradle or tomb of a second Genesis. Every drill and rover carries the responsibility to do no harm to what may be the only other home of life in our solar system. The study of analogues also reveals the universality of survival strategies. Whether in the hyper-arid Atacama, the frozen Antarctic desert, or the acidic mines of Spain, life finds similar solutions. Burrowing for shelter, slowing metabolism, forming protective biofilms, and using minerals as both substrate and energy source. These patterns suggest that if Martian life ever existed, it would follow parallel logic, not identical in form, but identical in principle. Biology adapts to physics. Chemistry converges towards stability. In the language of survival, the universe speaks one dialect. In contemplating the Martian subsurface, we are reminded that life need not cover a planet's surface to define its essence. The deep biosphere of Earth, vast, slow and unseen, offers a mirror for Mars's possible interior vitality. Beneath kilometers of rock, both worlds may share the same silent persistence. Even if no living cell remains on Mars, the chemical gradients, brines, and organics that still circulate there preserve the logic of life. The feedback between matter and energy that precedes biology and endures after it. The planet, in this sense, may still be alive in principle, if not in population. Ultimately, Mars's refugia represent the meeting point of hope and humility. They remind us that habitability is not a surface condition, but a planetary property, one that can retreat underground, yet never vanish entirely. The analogues on Earth show that life, when cornered, always finds the cracks, the shadows, the thin films where chemistry still breathes. If the red planet still harbors life, it does so in whispers, in the briny veins of frozen rock, in the darkness of caves, in the slow chemistry of stone. Mars, once an ocean world, may now be a cryptic biosphere, its life hidden but not extinguished, waiting for us to listen with the right instruments and the right reverence. And perhaps that is the deeper lesson of Martian refugia, that life's greatest strength is not expansion, but persistence, the ability to endure when the world collapses, to retreat into silence until the universe gives it voice again. In that endurance, Mars mirrors Earth, and both mirror the cosmos itself, a universe where, even in the coldest shadows, life refuses to die. Among all the dreams inspired by Mars, none captures the imagination more powerfully, or divides the scientific community more sharply, than the idea of terraforming. The vision is audacious, to transform the cold, dry, and irradiated Mars into a living world, one capable of sustaining liquid water, vegetation, and perhaps even human civilization. To some, terraforming represents the next logical step in humanity's cosmic evolution, the ultimate act of planetary stewardship. To others, it is an act of hubris, an intrusion into a world that may already harbor its own fragile ecology. Between these poles lies one of the great ethical and scientific questions of the 21st century. Should we, and could we, make Mars more like Earth? In theory, the process seems straightforward. Raise the temperature, thicken the atmosphere, and restore liquid water. Mars, after all, already has the essential ingredients: carbon dioxide, nitrogen, water ice, and sunlight. The planet's polar caps and subsurface deposits hold vast reserves of frozen CO2 and H2O. If released, they could, in principle, recreate a greenhouse effect strong enough to warm the planet. Early models proposed by Carl Sagan in the 1970s envisioned using dark dust or engineered microorganisms to lower the albedo of the polar ice caps, allowing them to absorb more sunlight and release CO2. The resulting greenhouse warming would trigger a runaway feedback loop: more heat, more ice sublimation, more atmospheric pressure, and eventually a breathable, or at least habitable, world. Modern analyses, however, have tempered that optimism. Mars simply lacks the inventory of volatile gases needed to sustain such transformation. A 2018 NASA study concluded that even if all known CO2 on Mars were liberated from ice caps, rocks, and soil, the resulting atmosphere would reach only about 1.2% of Earth's surface pressure, far short of what's required to stabilize liquid water. Without an artificial source of greenhouse gases, terraforming through natural feedback alone is physically unachievable with current technology. Yet where physics limits, imagination innovates. Several alternative terraforming strategies have emerged. ranging from the incremental to the grandiose. One concept involves manufacturing super greenhouse gases, chlorofluorocarbons or perfluorocarbons, in factories powered by nuclear or solar energy. These molecules are vastly more efficient heat trappers than CO2 and could, in theory, warm the planet enough to release trapped volatiles. Another idea is to deploy orbital mirrors, thin, reflective disks, kilometers wide, to direct sunlight onto polar regions, accelerating sublimation. Others have suggested detonating controlled thermonuclear devices to vaporize local ice caps, jump-starting an artificial greenhouse cycle. The engineering challenges are monumental, but the principle remains the same. Change Mars's energy balance until it crosses the threshold of habitability. At smaller scales, paraterraforming, creating local habitable zones under domes or within valleys, may offer a more realistic path. Instead of transforming an entire planet, we could build enclosed microenvironments, each with its own atmosphere and climate. The technology for this already exists in prototype form. Transparent aerogel structures can trap heat while allowing sunlight through, creating pockets of warmth on the Martian surface. These habitats could eventually evolve into interconnected biospheres, forming an archipelago of human livability across an otherwise unaltered world. In this sense, terraforming might not be an act of conquest, but of cohabitation. Learning to live with Mars rather than remake it entirely. A more controversial aspect of terraforming involves biological engineering, the deliberate introduction of life to Mars. Advocates argue that hardy microbes or genetically modified cyanobacteria could begin converting CO2 into oxygen, darkening the surface to absorb heat and enriching the soil with organic material. On Earth, extremophiles have colonized environments as harsh as those on Mars. Radiation-tolerant Deinococcus radiodurans, perchlorate-resistant halophiles, and cryophilic algae capable of photosynthesis at sub-zero temperatures. With modification, such organisms could serve as pioneer species, initiating a slow ecological cascade toward a biosphere. But this vision confronts an immediate ethical dilemma. What if Mars is not sterile? If native microbial life still exists in the subsurface, perhaps adapted to salt brines or ancient aquifers, introducing terrestrial organisms could annihilate it. Our own biosphere would become a contaminant, overwhelming a potentially unique second genesis. To seed Mars with Earth life might not be creation, but colonization, the erasure of an alien ecology before it can be understood. In the language of ethics, this is the principle of planetary preservation, that we must first know before we change, first protect before we populate. The debate over terraforming touches on deep philosophical currents. Some view humanity as a natural extension of cosmic evolution, life's instrument for spreading intelligence and complexity across the universe. In this view, transforming Mars is not desecration, but fulfillment. The universe becoming self-aware through us, shaping barren worlds into living ones. This cosmological humanism, championed by thinkers like Robert Zubrin and Martin Fogg, frames terraforming as the moral duty of a species capable of restoring life to dead planets. Opponents, however, counter that such reasoning risks repeating the ecological arrogance that scarred Earth. To impose our design on another planet is to project our anthropocentrism onto the cosmos. Mars, they argue, is not a blank canvas but a world with its own geological identity and evolutionary trajectory. Even if lifeless, it holds intrinsic value, a record of planetary history untainted by human interference. In this light, terraforming becomes an act of erasure, destroying data, context, and perhaps an entire natural philosophy of otherness. To preserve Mars is to honor the diversity of worlds, recognizing that not every planet is meant to be Earth. This ethical tension echoes a broader duality in human thought. Are we the gardeners of the cosmos or its invaders? Terraforming thus forces us to define what it means to be a technological species. Does mastery of nature entail responsibility to replicate it or to protect it? And if Mars truly is sterile, does it not become our moral duty to bring life where there is none, to ignite a new biosphere as the cosmos once did for us? Between these extremes lies the emerging concept of planetary stewardship, advocating for a balanced coexistence. To study first, to alter cautiously, and to preserve the planet's integrity while enabling sustainable presence. The governance of such decisions is not merely philosophical, but legal. The Outer Space Treaty of 1967, signed by all major spacefaring nations, declares that celestial bodies are the province of all humankind and prohibits harmful contamination. Yet the treaty offers no detailed mechanism for defining harm in the context of terraforming or biological seeding. Planetary protection guidelines, established by NASA and COSPAR, Committee on Space Research, mandate sterilization of spacecraft and strict containment for sample return missions. These rules embody a precautionary ethic to minimize interference until more is known. But as private companies and nations accelerate plans for Mars colonization, the legal vacuum widens. Who decides what constitutes ethical modification? Who speaks for Mars itself? The issue extends beyond microbes and minerals to the rights of worlds. Some ethicists argue that planets, as repositories of cosmic history, possess intrinsic moral status, a kind of geological dignity. To alter them without necessity is akin to vandalizing a sacred monument. Others contend that moral value arises only through the presence of life or consciousness. A dead world, by this reasoning, is ethically neutral terrain. Yet even this view demands caution, for ignorance of Mars's true state means we cannot yet know which it is. The principle of epistemic humility, acting only on knowledge we genuinely possess, should therefore guide all planetary intervention. Beyond the technical and ethical debates, terraforming reflects something profound about ourselves. It forces humanity to confront its relationship with creation. The urge to terraform may be less about saving Mars than redeeming Earth, a projection of our guilt and longing for mastery. As our own planet suffers from climate disruption, deforestation, and extinction, Mars becomes both laboratory and mirror. To imagine remaking another world is to confess that we have failed to care for our own. The irony is stark. Before we can breathe on Mars, we must learn to breathe responsibly on Earth. This realization reshapes the meaning of terraforming. Perhaps its purpose is not to create a second Earth, but to understand what makes the first one precious. The technologies of atmospheric regulation, greenhouse control, and ecological engineering developed for Mars could in turn help restore our own biosphere. In this sense, the act of preparing for another world becomes an act of self-reflection, a way of learning planetary humility through cosmic ambition. Still, within the dream of terraforming lies a deep human optimism. It is the belief that life is not confined to one planet, that we can be agents of cosmic renewal. If Mars truly is sterile, then giving it life would not be desecration, but continuation. The universe extending its living reach through us. Life, after all, is the only process known to resist entropy. To spread it is to participate in the universe's creative impulse. Yet, even this vision must bow to the principle of patience. To seed life responsibly, not recklessly. To awaken Mars, we must first listen to it, its chemistry, its history, its quiet persistence. Terraforming, if it ever comes, must emerge from understanding, not conquest. Every planet tells a story about possibility, the delicate balance between physics and biology, chaos and order, chance and continuity. Mars, more than any other world in our solar system, tells the story of what might have been. It was once warm enough for rivers, stable enough for lakes, and geologically active enough to recycle carbon and water. It came close to sustaining a long-lived biosphere, and then lost it. In that loss lies its greatest lesson, that habitability is not a permanent state, but a fragile equilibrium between planetary energy, atmosphere, and time. To understand Mars is to understand the fine line that separates a living world from a lifeless one. When we compare Mars to Earth, the similarities are haunting. Both worlds, formed from the same solar nebula, share nearly identical chemical compositions, and once had global hydrospheres and active climates. Yet while Earth flourished, Mars faltered. The reason, scientists now know, lies partly in scale. Mars, at half Earth's diameter and 1/10 its mass, cooled too quickly. Its smaller gravity allowed gases to escape more easily, and its molten core solidified within 1 billion years, shutting down the planetary dynamo that generated its magnetic field. Without that magnetic shield, the solar wind began stripping the atmosphere atom by atom, eroding its pressure until liquid water could no longer persist on the surface. The transformation was irreversible. What began as a world of clouds and rivers ended as a desert of dust and ice. This planetary divergence illustrates the first principle of habitability: stability of energy and protection. Life requires not only liquid water and carbon chemistry, but also a long-term energy source, geological or stellar, that maintains equilibrium between radiation and renewal. Mars reminds us that size matters. Small planets lose heat quickly, large ones retain it. In this sense, Mars is the archetype of the failed Earth, a world that had all the right ingredients, but insufficient endurance. Its history offers a cautionary mirror for exoplanet studies. Habitability is not binary, but temporal, dependent on how long a world can keep its internal fires alive. The thin Martian atmosphere, barely 0.6% of Earth's pressure, holds the ghost of its former self. Isotopic ratios of argon, carbon, and oxygen, measured by the Curiosity rover and MAVEN orbiter, show enrichment in heavier isotopes, evidence of lighter ones lost to space. Over billions of years, ultraviolet radiation and solar wind sputtering eroded the air, while the remaining CO2 froze into polar caps or became locked in carbonate rocks. The result is a planet whose climate feedback loops have collapsed. The carbon silicate cycle, which stabilizes Earth's temperature through volcanism and weathering, is effectively extinct on Mars. Without active plate tectonics to recycle carbon, its climate drifted toward equilibrium with the void. From this, Mars teaches a second principle of habitability: planetary metabolism, the capacity for self-regulation through geological and atmospheric feedback. Earth's climate remains habitable not because it is unchanging, but because it can change back. When temperatures rise, weathering draws down CO2. When they fall, volcanism replenishes it. Mars, having lost its geological respiration, suffocated not from catastrophe, but from stillness. A habitable world must therefore be dynamically alive, a system of ongoing exchange between rock, air, and ocean. Life thrives not on balance, but on the constant oscillation that sustains it. Mars also teaches us that water alone is not enough. For years, the mantra of astrobiology was simple: follow the water. The logic was sound. Wherever liquid water exists on Earth, life follows. Yet Mars challenges that assumption. Its ancient riverbeds, deltas, and sedimentary rocks record billions of years of aqueous history, but so far no direct evidence of life has emerged. This suggests that habitability and inhabitedness are not synonymous. Water may create opportunity, but not inevitability. For life to begin, it must exploit chemical disequilibria, energy gradients between oxidants and reductants. On early Earth, these gradients flourished in hydrothermal vents and volcanic basins. On Mars, they may have been too brief or too weak to sustain self-organization. In this way, Mars embodies the threshold problem of life, the fine distinction between a habitable planet and a living one. Nevertheless, the persistence of subsurface ice and hydrated minerals proves that water remains part of the Martian system. The cryosphere and deep crust may still host brines, offering potential habitats even today. This teaches a third principle, that habitability can retreat without vanishing. Life, if it ever existed on Mars, may have followed the water underground, adapting to the planet's cooling and desiccation. The surface became sterile, but the subsurface could remain chemically active. This layered habitability, the idea that planets can shift their biological zones inward as they age, has profound implications for the search for life elsewhere. It suggests that a planet's biosphere may persist long after its surface dies. The study of Mars has reshaped our understanding of exoplanets more profoundly than any telescope. Its trajectory from wet to dry provides a natural experiment in planetary evolution. Many rocky worlds discovered in other systems likely follow similar paths. Born with oceans, stripped by radiation, frozen into silence. By modeling Mars's loss of atmosphere and magnetism, scientists can estimate how quickly habitability fades under various stellar conditions. For example, planets orbiting red dwarfs, common in our galaxy, face intense stellar winds and flares. Without protective magnetic fields, they could become super-Mars worlds, losing air and water within a few 100 million years. Conversely, those with stronger gravity or internal heat may retain their atmospheres for billions of years, becoming super-Earths. Mars thus serves as the control case, the benchmark for understanding why some planets survive as living worlds, while others become tombs. Mars also teaches humility in the search for biosignatures. The ambiguous results from Viking, the trace organics from Curiosity, and the elusive methane plumes remind us that detection is not discovery. Biology leaves traces that chemistry can mimic. The challenge is not just to find molecules of life, but to distinguish them from those of non-life. On Mars, ultraviolet radiation, cosmic rays, and perchlorates can all generate false positives. The planet warns us that context is everything, that life's signature must be read within its geological and chemical environment. This lesson now shapes how we design future missions, from ExoMars's deep drilling to the Mars Sample Return campaign. It also informs how we interpret exoplanet atmospheres. A spectrum showing oxygen or methane alone is not proof of life, but a puzzle requiring planetary context. In this sense, Mars has matured astrobiology from enthusiasm to discipline. One of Mars's most profound teachings is that habitability is not static, but continuum-based. Early Mars was Earth-like, with a dense atmosphere and global hydrology. Middle Mars was transitional, episodic floods, volcanic eruptions, transient warmth. Modern Mars is cold, thin-aired, and oxidizing, yet not chemically dead. These stages form a spectrum of planetary vitality, from full biological potential to geochemical twilight. The same continuum likely exists across the galaxy. Planets begin vibrant, pass through crises, and either stabilize or fade. Mars shows us that life may not end abruptly, but fade through stages of decline, adapting, receding, and possibly surviving in hidden niches. The universe, therefore, may be filled not only with living worlds, but with half-living ones, planets in metabolic limbo, echoing their biological pasts through chemistry. Perhaps the most haunting lesson of Mars is existential. Its red deserts mirror our own future. Earth, too, will one day lose its magnetic field, its atmosphere, and its oceans. The sun will brighten, the climate will shift, and the biosphere will wither. Mars offers a preview of that distant destiny, a glimpse of what happens when feedbacks fail. Yet it also offers hope that life can endure change by adaptation, migration, or transformation. If microbial life once flourished on Mars and retreated underground, it teaches us that resilience is written into biology itself. Mars thus becomes both cautionary tale and testament to endurance, the story of a planet that could not sustain life forever, but perhaps still sustains it in secret. On a more immediate level, Mars reminds us of our fragility as planetary engineers. The atmospheric loss, once gradual and natural, finds echo in Earth's human-driven climate change. The mechanisms differ, but the outcome, destabilization of equilibrium, is the same. Mars teaches humility, that a planet's habitability can be lost, and that no feedback system is invincible. In the silence of its dunes, Mars whispers a warning to Earth. Climate is a privilege, not a guarantee. Beyond science, Mars teaches us a philosophy of worlds. It shows that life and planet are not separate, but co-evolving entities, one shaping and being shaped by the other. Earth is not alive on its surface. It is alive as a system. Mars may have shared this systemic vitality once, and may still retain echoes of it deep underground. From this arises a new definition of habitability. Not merely the ability to host life, but the ability to sustain the dialogue between biology and geology. A habitable planet is one that converses, where matter, energy, and feedback remain in motion. When that conversation ceases, the planet falls silent. This insight reframes how we view the universe. The cosmos may be full of worlds like Mars, ancient, quiet, yet chemically eloquent. Their silence is not emptiness, but memory, the lingering afterglow of conditions that once supported vitality. To explore them is to read the fossil record of cosmic habitability. Every desert plain, every frozen crater, every buried ice sheet is a page in that record. Through Mars, we learn to listen to planets not just as environments, but as narratives. Stories of how matter once learned to organize itself into meaning. Ultimately, what Mars teaches about planetary habitability is that it is both ephemeral and universal. The forces that made Mars habitable once, volcanism, magnetism, chemistry, water, are the same that made Earth a cradle of life. Their failure on Mars reveals their importance here. Mars is therefore not merely an object of exploration, but a mirror of understanding, a natural experiment in planetary mortality. Its study has forced science to refine the very definition of life's conditions, to search beyond simple checklists of water and temperature, and to embrace complexity, feedback, and time as the true pillars of habitability. In the end, Mars stands as both teacher and warning. It shows us that life is not the default outcome of habitability, but its highest achievement, fragile, contingent, and rare. Yet it also shows us that the potential for life is woven into the cosmos itself, waiting for the right balance of heat, water, and chemistry to awaken. Mars may have failed to sustain that balance, but in doing so, it has given us a map of what to look for and what to protect. When we gaze at its red horizon, we are not merely looking at another world. We are looking at the reflection of our own, at what happens when the dialogue between planet and life breaks. Mars's silence is not final. It is instructive. It teaches us how thin the thread of habitability truly is, and how miraculous it is that on one small blue world, that thread still holds. The exoplanet revolution, worlds without number. Among all the moons of the solar system, none defies expectation more completely than Titan, Saturn's largest satellite and the second largest moon after Ganymede. With its golden haze, thick atmosphere, and sculpted surface, Titan appears at first glance almost planetary. It has rivers, lakes, rain, dunes, and seasons. Yet these familiar features are made of substances utterly alien to Earth. Titan's rain is not water but liquid methane and ethane. Its rivers are hydrocarbons flowing through frozen plains of water ice. And its lakes shimmer not with blue, but with the oily hue of petroleum seas. In Titan, nature has built a mirror world, eerily Earth-like in form, but composed of entirely different chemistry. To explore Titan is to glimpse how life, weather, and geology might operate under the laws of another element. Titan was discovered by Christian Huygens in 1655, but its true nature remained hidden until the space age. When the Voyager 1 and 2 spacecraft flew past Saturn in 1980 to 81, they revealed a world wrapped in a dense orange atmosphere, so opaque that not even a hint of its surface could be seen. The surprise was immediate. No other moon in the solar system had such a thick atmosphere. Titan's air is about 1.5 times denser than Earth's, composed mostly of nitrogen, approximately 95%, with methane making up most of the remainder. This mixture is strikingly similar to Earth's primordial atmosphere before the rise of oxygen, suggesting Titan as a kind of time capsule for early planetary conditions. The presence of methane, however, raised a paradox. At Titan's frigid surface temperature of about -179 degrees Celsius, 94 Kelvin, sunlight should break down methane into hydrogen and complex hydrocarbons within tens of millions of years. Yet Titan's methane persists. This means it must be replenished continuously, either through outgassing from the interior or cryovolcanic activity. This steady renewal feeds a methane-based hydrological cycle analogous to Earth's water cycle, complete with evaporation, cloud formation, rainfall, and surface runoff. Titan, in essence, is the only other world known with a stable, liquid cycle on its surface. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, revolutionized our view of Titan. Using radar mapping and near-infrared imaging capable of penetrating the haze, Cassini discovered vast lakes and seas concentrated near Titan's North Pole. The largest, Kraken Mare, spans more than 1,000 kilometers, larger than the Caspian Sea, and is filled with liquid methane and ethane. Smaller bodies, such as Ligeia Mare and Punga Mare, dot the polar regions, interconnected by channels and bays. These seas are not static. They exhibit changing shorelines, waves, and even tides driven by Saturn's gravity. At lower latitudes, Cassini's radar revealed branching valleys and dendritic river systems, features unmistakably shaped by liquid erosion. Some of these channels extend for hundreds of kilometers, flowing toward the polar basins. The Huygens probe, which parachuted through Titan's atmosphere in January 2005, confirmed this pattern on the ground. It landed in a dried-up floodplain strewn with rounded pebbles of water ice, eroded smooth by methane rivers. In every way, Titan's landscape is geologically active and hydrologically alive. But its hydrology is one of hydrocarbons, not water. Methane on Titan behaves exactly as water does on Earth, obeying the same physics of phase change. It evaporates from lakes and wet soil, condenses into clouds, and falls back as rain. This methane weather shapes Titan's surface through erosion, sediment transport, and deposition. Cassini's observations of bright cloud formations over the poles and equator revealed storms sweeping across the surface, sometimes triggering torrential methane downpours that darken vast regions. The rainfall carves channels and fills temporary lakes, replenishing the polar seas in cycles that may span decades or even centuries. Titan's seasons, governed by Saturn's 29.5-year orbit around the Sun, further modulate this weather. During northern summer, sunlight, weak though it is, evaporates methane from southern reservoirs, driving atmospheric circulation toward the north. When seasons shift, the pattern reverses. This slow global rhythm mirrors Earth's monsoon cycles, but plays out on cosmic timescales. Titan's atmosphere, though sluggish and cold, is anything but static. It breathes methane just as Earth breathes water. Intriguingly, Cassini detected occasional lightning-like discharges and hints of convective activity within Titan's clouds. Although electrical storms are rare, they could catalyze chemical reactions, producing hydrogen cyanide, acetylene, and other prebiotic precursors. In this way, Titan's meteorology becomes both a sculptor of landscapes and a laboratory for organic synthesis. Beneath Titan's lakes and plains lies a crust of water ice as hard as granite, underlain by an ammonia water ocean that may extend for hundreds of kilometers. The solid surface behaves like rock, while the internal ocean provides buoyancy and potential movement. This hybrid structure gives rise to cryovolcanism, volcanic-like processes where slurries of water, ammonia, and organics erupt instead of molten rock. Cassini's radar and imaging systems found possible cryovolcanic domes and flow features such as Doom Mons and Sotra Patera, suggesting that Titan's interior remains active. These outflows could deliver fresh methane and ammonia to the surface, replenishing the atmosphere and feeding the hydrological cycle. Some models suggest that Titan's methane reserves are replenished by degassing from the interior, where carbon compounds are trapped in clathrate hydrates, crystalline cages of water that release gas when heated or deformed. In this sense, Titan's geology and meteorology are one interconnected system, where internal processes sustain external weather. Cryovolcanic flows also provide transient conditions, where liquid water might exist on or near the surface for short periods. In such environments, organic solids raining from the sky could mix with warm water, forming chemical crucibles for complex synthesis, miniature laboratories that echo Earth's early prebiotic chemistry. Standing hypothetically on Titan's surface would be a surreal experience. The sky would glow dimly orange, filtered through a haze of organic aerosols. The sun would appear a tiny pale disk, its light barely 1% as bright as on Earth. The temperature would hover around minus 179 degrees Celsius, cold enough to freeze nitrogen, yet the pressure would feel comfortably Earth-like. Lakes would glimmer like black mirrors, their waves sluggish in the dense atmosphere. Rain would fall not in drops of water but liquid methane, evaporating slowly into mist. Each breath of that atmosphere would be deathly toxic, but the environment itself would feel paradoxically calm, stable, almost peaceful. Titan, in many ways, is a chemical reflection of Earth, a twin shaped by the same physical laws, but different ingredients. Where Earth's cycle is water-based, Titan's is hydrocarbon-based. Where our rocks are silicates, Titan's are ice. Where our clouds are vapor, Titan's are methane. This mirroring fascinates planetary scientists because it suggests that planetary processes are universal, independent of composition. Weather, erosion, tectonics, and possibly even biochemistry are expressions of physics, and physics is impartial to chemistry. Titan's atmosphere remains in delicate equilibrium, its methane constantly renewed and destroyed. Solar ultraviolet radiation breaks methane into radicals that combine into more complex hydrocarbons: ethane, propane, acetylene, and hydrogen cyanide, which eventually fall as organic snow onto the surface. These deposits form dunes and plains that encircle the equator, sculpted by slow winds. The global circulation redistributes methane between hemispheres, forming a closed hydrological loop that has likely persisted for millions of years. Without active replenishment, Titan's methane would vanish within 10 to 20 million years, a blink in geological time. Its persistence implies ongoing outgassing from the interior, confirming that Titan is not a frozen relic, but a living planet in chemical flux. This methane-based cycle may even mirror the carbon cycle on Earth, where volcanic CO2 release balances atmospheric loss. Titan thus serves as a template for atmospheric self-regulation, a world that maintains climate through organic, rather than mineral feedbacks. Titan's lakes and rivers of methane represent more than geological curiosity. They are potential habitats for exotic forms of life. Though far too cold for liquid water, Titan's surface offers liquid hydrocarbons, solvents capable of supporting chemistry, albeit very different from ours. In such an environment, cell membranes might be built not from phospholipids, but from acrylonitrile-based structures, forming azotosomes stable in liquid methane. Energy metabolism could proceed through reactions between hydrogen and acetylene, rather than oxygen and carbon. These possibilities, while speculative, are grounded in real chemistry. Laboratory studies have shown that complex organic molecules can form membranes and metabolic analogues even at cryogenic temperatures. Titan may therefore host an alternative biochemistry, a second genesis of life built not on water, but on methane. If true, Titan would demonstrate that life is a universal function of chemistry, not a unique outcome of water. Its lakes could host microbial analogues that operate on energy flows invisible to us, slow, cold, and alien, yet alive, by any scientific definition. The question is not whether life as we know it exists there, but whether life as it could be does. In the broader search for life, Titan stands as the counterpoint to the ocean worlds. Where Europa and Enceladus represent warm, hidden oceans sustained by water, Titan represents a surface biosphere in the deep freeze. A laboratory of carbon-based chemistry proceeding without heat or light. Its existence expands the definition of habitability beyond temperature and solvent type, showing that planets and moons can follow entirely different chemical pathways and still sustain active cycles of renewal. Titan is, in a sense, a natural experiment in alternative planetary evolution. It challenges every anthropocentric assumption about where and how life can exist. It reminds us that habitability is not a narrow zone around a star, but a broad spectrum of physical and chemical balance. That the cosmos may host methane worlds, ammonia worlds, or even nitrogen oceans, each with its own rules of biology. When future explorers arrive on Titan, as the Dragonfly mission will in the coming decades, they will not merely study a distant moon. They will step into a living simulation of alien chemistry, a world that has already reinvented the concept of a hydrosphere. Titan's methane lakes and hydrocarbon rain tell us one simple truth: that life, in whatever form it takes, will always find a way to flow. High above Titan's methane seas, sunlight meets chemistry in a slow, unending alchemy. Despite receiving only 1% of the sunlight that warms Earth, Titan's upper atmosphere glows with activity, a chemical symphony conducted by ultraviolet radiation and cosmic particles. Here, at altitudes of hundreds of kilometers, simple molecules like nitrogen, N2, and methane, CH4, are broken apart by solar photons and Saturn's magnetospheric electrons, initiating an astonishing cascade of reactions. From this photochemical firestorm emerge complex hydrocarbons, nitriles and organics that eventually drift downward, condensing into aerosols and falling like orange snow onto the surface. This process is more than atmospheric chemistry. It is prebiotic chemistry in action, a glimpse into how the building blocks of life may assemble even on worlds devoid of water and light. Titan's atmosphere, cold and alien though it may be, behaves like a vast planetary laboratory recreating in slow motion the chemical dawn that once preceded life on Earth. Titan's atmosphere begins at about 1,000 kilometers above the surface and extends far into space. There, solar ultraviolet UV radiation and charged particles from Saturn's magnetosphere collide with nitrogen and methane molecules, breaking their bonds through photolysis and ionization. This creates a zoo of reactive fragments: nitrogen atoms, methyl radicals, CH3, and ions like N2+ and CH4+. These fragments recombine in myriad ways, forming new molecules such as hydrogen cyanide, HCN, acetylene, C2H2, ethylene, C2H4, and benzene, C6H6. Many of these products are aromatic hydrocarbons, the same molecular rings found in amino acids and nucleobases. As they grow in complexity, they polymerize into tholins, reddish organic solids that dominate Titan's haze. Tholins, first synthesized in laboratory experiments by Carl Sagan and Bishan Kare in the 1970s, are the key to Titan's color and its chemical intrigue. They consist of nitrogen-rich macromolecules, irregular chains, and rings of carbon, hydrogen, and nitrogen, with properties intermediate between simple hydrocarbons and biological polymers. These substances are thought to be prebiotic analogues, chemical intermediates on the path toward life's molecular complexity. Titan's haze is not uniform, but stratified into multiple layers, each corresponding to different stages of chemical evolution. The upper atmosphere, above 800 kilometers, is dominated by ion-neutral chemistry, where solar photons and cosmic rays drive reactions among charged particles. Below this, at altitudes between 300 to 500 kilometers, neutral reactions take over as radicals recombine, forming increasingly complex hydrocarbons and nitriles. At around 100 to 200 kilometers, these molecules condense into aerosols, tiny particles that aggregate into larger clumps, scattering sunlight and giving Titan its orange hue. Each aerosol particle is a microcosm of chemical diversity. Laboratory simulations show that such grains can contain amino acid precursors, carboxylic acids, and polycyclic aromatic hydrocarbons, PAHs. As they drift downward, they may undergo further processing by methane rain or surface liquids, releasing soluble organics into Titan's rivers and lakes. In this sense, Titan's haze acts as both a factory and a delivery system, continually seeding the surface with complex carbon chemistry. Cassini's UVIS, ultraviolet imaging spectrograph, and INMS, ion and neutral mass spectrometer, provided direct evidence of this photochemical cascade. They detected heavy ions and complex hydrocarbons at altitudes exceeding 900 kilometers, some with masses over 1,000 atomic units, far larger than expected in a planetary atmosphere. These observations suggest that Titan's upper atmosphere operates like an organic plasma reactor, generating polymeric molecules akin to soot or organic aerosols on Earth, but under much colder conditions. Nitrogen is the hidden architect of Titan's chemistry. Unlike Mars or Venus, whose atmospheres are dominated by carbon dioxide, Titan's nitrogen-methane blend mirrors the reducing conditions believed to exist on early Earth before oxygenation. Nitrogen participates in reactions that form nitriles, such as acetonitrile, CH3CN, and hydrogen cyanide, HCN, both of which are precursors to amino acids and nucleic acids. HCN is especially significant. On Earth, it was likely a central reagent in prebiotic synthesis, a molecule capable of forming adenine, one of the bases of DNA and RNA, through polymerization. Titan's atmosphere produces vast amounts of HCN, that condense and fall onto the surface, accumulating over geological time. Models estimate Titan's surface could be coated with millions of tons of HCN polymers, forming reservoirs of prebiotic potential awaiting liquid water or another solvent to activate them. In Titan's cold environment, these nitriles remain stable for eons, preserved like fossils of chemistry in a freezer. If Titan's crust ever experiences transient melting, through impacts, cryovolcanism, or tidal heating, these compounds could dissolve, react, and possibly progress toward biochemical organization. Titan thus represents not just an analogue of early Earth, but perhaps a parallel experiment, a planet-scale test of how far organic complexity can evolve in the absence of biology. Because direct sampling is limited, scientists have turned laboratories into miniature Titans. Experiments simulating Titan's atmosphere in cold chambers with methane, nitrogen, and ultraviolet light reproduce the formation of tholins and related organics. When these synthetic tholins are dissolved in liquid water, they yield amino acids, urea, and nucleobase analogues, fundamental precursors of life. This demonstrates that Titan's haze particles, though formed in an anhydrous environment, contained latent chemistry that could spring to life in the presence of liquid water or ammonia. One remarkable experiment conducted by the University of Arizona's Astrobiology Center replicated Titan's atmospheric chemistry under electrical discharge. The resulting tholin samples, when analyzed, revealed hundreds of distinct molecular species, some containing oxygen, even though the input gas mixture lacked it. This oxygen incorporation likely occurred through reaction with trace water or carbon dioxide impurities, showing how readily Titan-like chemistry can diversify. The results hint that oxygen-bearing organics may form naturally on Titan through cosmic ray interactions or surface processing. The products of photochemistry, the tholins, nitriles, and hydrocarbons, eventually coagulate and descend. Cassini's radar and spectrometers detected extensive organic deposits across Titan's equatorial regions, forming vast dune fields composed of complex molecules. These dunes stretch for thousands of kilometers, shaped by winds into parallel ridges. Unlike terrestrial sand, Titan's dunes consist of grains of solid hydrocarbons, possibly mixtures of benzene, acetylene, and HCN polymers. Each grain represents a frozen droplet of atmospheric chemistry, a record of reactions that began hundreds of kilometers above. When methane rain falls upon these dunes, it may partially dissolve the organic solids, forming liquid phase reactions in the rivers and lakes. In this way, Titan's climate connects atmosphere and surface in a planet-wide cycle of organic transformation, photochemistry above, hydrology below, and constant feedback between the two. The equatorial dunes act as Titan's chemical archive, while the polar lakes function as its solvent laboratory. Together they create a two-stage system, production in the sky, processing on the ground, that mimics the conditions thought to have prevailed on the young Earth before biology emerged. For astrobiologists, Titan is a living memory of Earth's past, a frozen analogue of the prebiotic era. Billions of years ago, before oxygen filled our atmosphere, Earth too was dominated by nitrogen, methane, and ammonia. Lightning, ultraviolet light, and volcanic gases drove similar photochemical reactions, producing a primordial haze that rained organic compounds into warm oceans. Titan's current atmosphere preserves that same chemistry, but slowed by cold and shielded from water's reactivity. In this way, Titan allows scientists to study the prebiotic Earth in real time, frozen at an earlier chapter of planetary evolution. The resemblance is more than poetic. Measurements of isotopic ratios on Titan indicate that its nitrogen likely originated from ammonia, NH3, photodissociation, the same pathway that may have produced Earth's nitrogen atmosphere. The coexistence of methane and nitrogen in a reducing environment provides the exact conditions for Miller-Urey-type synthesis, the spontaneous creation of amino acids under energy input. On Earth, this chemistry gave rise to life. On Titan, it remains suspended, a grand experiment paused at the threshold of biology. While Titan receives little solar energy, its thick atmosphere traps and redistributes what little sunlight penetrates, maintaining a complex energy budget. Photochemical reactions occur continuously, powered by ultraviolet photons and cosmic rays, which penetrate even the dense haze. The resulting radicals and ions sustain chemical cycles that never truly stop. Titan's atmosphere is effectively self-renewing, constantly rebuilding its methane, organics, and haze layers. Moreover, the descent of organic aerosols deposits chemical energy on the surface in the form of metastable molecules, compounds rich in stored potential energy, like acetylene and hydrogen cyanide. When these molecules encounter oxidants or even small amounts of heat, they can release energy through exothermic reactions. Titan's landscape is therefore chemically active at every level, a slow-burning planet where energy and matter are always out of equilibrium. The essential condition for life. Titan's photochemistry provides a model for exoatmospheres around distant worlds. Many exoplanets, especially those orbiting red dwarfs, experience intense ultraviolet radiation and possess methane or nitrogen-rich atmospheres. The haze layers formed by photochemistry can obscure starlight, complicating telescope observations. By studying Titan, scientists learn how such hazes affect spectra and what chemical fingerprints they produce. Titan thus serves as a template for interpreting alien skies, showing how light interacts with complex organic aerosols. The lessons extend beyond the solar system, guiding the next generation of missions, from the James Webb Space Telescope to future exoplanet probes, in recognizing atmospheric signatures of both prebiotic and biotic chemistry. In Titan's atmosphere, we witness the continuum between physics, chemistry, and biology. The same photochemical processes that sculpt haze also sculpt potential. Molecules once considered dead, methane, nitrogen, carbon dioxide, become precursors to life's alphabet when given energy and time. Titan's sky, glowing with organic mist, teaches that life's chemistry does not require warmth or sunlight. It requires only complexity and imbalance. Every orange particle drifting down through that cold sky is a frozen possibility, a relic of universal chemistry that may one day awaken under the right conditions. Titan shows us that the universe's default state is not lifelessness, but chemical creativity. That planets naturally evolve toward molecular richness, even without biology's guidance. In Titan's haze, the line between atmosphere and life blurs. It is both a veil and a womb, the planetary placenta of organic evolution. What began as starlight ends as potential life. And in that transformation lies Titan's greatest revelation. That even in darkness, the chemistry of creation never ceases. At first glance, Titan seems far too cold to host life. Its surface temperature hovers around -179 degrees Celsius, 94 Kelvin. Its lakes are filled with liquid methane and ethane, and its water is locked into rock-hard ice. Yet Titan challenges a central assumption in biology, that liquid water is the universal prerequisite for life. On this frigid moon, methane flows as freely as water does on Earth, cycling through clouds, rivers, and rain. If life depends fundamentally on the presence of a solvent that enables chemistry, then why not methane? Could alien organisms arise whose cells are composed not of water-based fluids, but of hydrocarbon matrices, thriving in cryogenic lakes under a golden sky? This question cuts to the heart of astrobiology. It asks whether life is defined by specific chemistry or by universal principles of organization, whether the laws of thermodynamics and molecular interaction can generate complexity in entirely different chemical domains. Titan, as the only known world with stable surface liquids besides Earth, offers the first real test of this idea. Every living system on Earth depends on a solvent, a medium that allows molecules to dissolve, move, and react. Water, with its polar structure, hydrogen bonds, and wide liquid temperature range, is ideal. It dissolves salts and organics, stabilizes macromolecules, and facilitates acid-base reactions essential to metabolism. But water is not unique in its ability to serve as a solvent. It is simply abundant and well-suited to Earth's temperature range. Theoretically, other solvents could perform similar functions under different physical conditions. Ammonia, formamide, sulfuric acid, and even supercritical carbon dioxide have been proposed as alternatives. Among them, liquid methane and ethane stand out, because they are abundant in the outer solar system, and exist naturally as liquids on Titan. The question, then, is not whether methane can dissolve organic molecules. It can. But whether it can support the complex chemical dynamics necessary for life. Titan's surface liquids are composed primarily of methane, CH4, and ethane, C2H6, with traces of nitrogen, propane, and dissolved atmospheric gases, like hydrogen and acetylene. These hydrocarbons are nonpolar, meaning they lack the electric charge separation that makes water such a versatile solvent. In water, ions and polar molecules readily dissolve, forming reactive environments. In methane, such polar chemistry is suppressed. This creates a paradox. Titan's lakes are chemically rich but reaction poor. Molecules do not easily interact because the solvent's low polarity prevents charge-based catalysis. Yet this limitation may not preclude life. It may simply favor a different style of chemistry. Nonpolar solvents stabilize molecules that would be unstable in water, allowing long-chain hydrocarbons, radicals, or azides to persist. In such an environment, life might evolve to use covalent bonding networks rather than ionic reactions. Instead of water's acid-base equilibrium, metabolism could rely on redox reactions involving hydrogen, acetylene, and nitriles, processes already abundant in Titan's atmosphere and surface. The key lies in thermodynamic disequilibrium, the imbalance between available energy sources and chemical stability. Titan's atmosphere and lakes are rife with such imbalances. Methane and acetylene coexist with hydrogen and nitrogen, forming an energetic mismatch that life could exploit. Indeed, models predict that if Titan harbored microbes consuming hydrogen and acetylene, their metabolic byproducts would subtly alter the atmospheric composition. Intriguingly, Cassini measurements showed less hydrogen near Titan's surface than expected, a tantalizing clue, though not yet evidence, of biological activity. In 2015, a team of researchers at Cornell University proposed a groundbreaking model for methane-based life, the azotosome, a hypothetical cell membrane capable of functioning in liquid methane. On Earth, biological membranes are formed by phospholipid bilayers, which rely on the polar nature of water to assemble spontaneously. In methane, polar lipids would fail. The Cornell team, using molecular dynamics simulations, identified an alternative, acrylonitrile, C2H3CN, a molecule abundant in Titan's atmosphere and detected by Cassini's radar spectrometer. Acrylonitrile molecules can form flexible, stable membranes in liquid methane, analogous to lipid membranes in water. These azotosomes would be able to contain internal chemistry, exchange small molecules, and maintain structural integrity at Titan's surface temperature. They would not require proteins or phosphates. Their stability arises purely from physical interactions between hydrocarbon molecules. This discovery transformed the conversation about Titan's habitability. It provided a plausible mechanism for cell-like organization in a methane solvent. If azotosomes can exist, then life could, in principle, assemble from Titan's atmospheric organics without ever needing liquid water. Such life would operate at cryogenic speeds, its metabolism unfolding 1,000 times slower than ours, yet perfectly in equilibrium with its environment. At -179 degrees Celsius, the chemistry of life would proceed with extreme slowness. Reaction rates in methane are several orders of magnitude lower than in water. However, time on Titan is abundant. Processes that take seconds on Earth could unfold over millennia there. The stability of molecules at such low temperatures may even favor long-term molecular evolution. Without heat to degrade complex compounds, Titan's organic inventory accumulates and persists. Energy, though sparse, is available. The oxidation of hydrogen with acetylene or ethane yields small but significant energy per reaction. Cosmic rays and ultraviolet photons also provide continual energy input. Life could thus evolve to exploit tiny gradients, operating near thermodynamic equilibrium, what some researchers call life at the edge of energy. Such organisms would be slow, efficient, and enduring, biochemical glaciers rather than burning fires. Metabolism in liquid methane might resemble solid-state chemistry more than fluid biochemistry. Reactions could occur along surfaces, within membranes, or through polymer exchange. Catalysis might rely on quantum tunneling or radical intermediates. In this framework, life is a pattern of organization, not a specific chemistry. If molecules can self-organize, maintain boundaries, and use environmental energy to reproduce, they fulfill the functional definition of life. The key challenge for Titan-like life is the solubility of large biomolecules. Polar polymers, such as DNA or proteins, would be insoluble in methane, but non-polar analogues, polyethers, polyimines, or hydrocarbon chains with reactive sites, could substitute. Titan's rich atmospheric nitriles provide the raw materials for such alternate polymers. Thus, methane life might not be cellular in the traditional sense. It could exist as gel-like networks or surface-bound films, exchanging materials through diffusion or electrostatic gradients. The line between organism and environment might blur, just as early terrestrial life was once indistinguishable from its geochemical surroundings. On Titan, life may still be in the process of becoming, chemistry on the verge of biology. If methane-based life exists, how might we detect it? Traditional biosignatures, oxygen, carbon dioxide, or chlorophyll-like pigments would not apply. Instead, scientists look for chemical anomalies inconsistent with equilibrium. For example, Cassini detected an unexpected depletion of acetylene and hydrogen near Titan's surface, leading to speculation that microbes could be consuming these gases as food. Models suggest that a hydrogen-eating organism could produce measurable gradients in the atmosphere. While these anomalies might also have abiotic explanations, they demonstrate that Titan's chemistry is out of balance, a classic hallmark of metabolic potential. Future missions, such as Dragonfly, will investigate these anomalies more closely. Equipped with mass spectrometers and surface sampling tools, Dragonfly will measure isotopic ratios, organic complexity, and molecular chirality, subtle fingerprints of biological processing. If Titanian life exists, its metabolism may leave traces in the ratios of carbon or hydrogen isotopes, just as terrestrial life fractionates isotopes during metabolism. Even the detection of azotosome-like structures in Titan sands would be revolutionary, confirming that cell-like organization is possible in methane. Even if Titan's lakes do not currently host active life, they may preserve the remnants or potential of it. Periodic impacts or cryovolcanic eruptions could transiently melt subsurface water-ammonia mixtures, creating warm oases where tholins and nitriles react into more complex organics. When these ponds refreeze, their chemical products could survive, awaiting reactivation. In this sense, Titan could act as a chemical memory, a planet constantly attempting and preserving the steps toward biogenesis. Such chemistry might not yet have crossed the boundary into metabolism, but it could be on the threshold, a proto-life environment, perpetually rehearsing the origin of life without ever achieving it. For astrobiology, this is just as valuable, for it shows how life begins, not merely how it endures. Titan's cold slowness is its gift. It preserves the molecular fossils of processes long erased on warmer worlds. If life can indeed exist in liquid methane, the implications are staggering. It would mean that life is not an accident of water, but an emergent property of the universe. Every solvent, every temperature range, every chemical niche could give rise to its own version of biology. The cosmos would be a mosaic of biochemical species: water life, ammonia life, methane life, each expressing the same universal logic of energy and organization. Earth's biology would be but one dialect in a vast chemical language spoken across the galaxy. This possibility forces us to rethink the definition of habitability. The habitable zone around stars, the so-called Goldilocks region, may apply only to water-based life. But for methane life, the habitable zone shifts outward to the realm of cold giants and their moons. Titan may therefore represent not an anomaly, but a prototype, one of countless cold worlds, orbiting distant suns where life follows chemistry we cannot yet imagine. Methane, the simplest hydrocarbon, is also one of the most combustible substances known. On Titan, however, it exists peacefully as liquid and gas, a paradoxical ocean of fuel without fire, because there is no free oxygen to ignite it. This irony captures the essence of Titan's mystery. It is a world full of potential energy, chemically rich yet quiescent, waiting for a spark, whether geological, chemical, or biological, to unleash it. If life ever arises there, it will be a cold flame, burning not with heat, but with order, feeding on imbalance at the edge of freezing infinity. In this way, Titan reminds us that life is not confined by temperature or substance, but by imagination. Methane, once considered sterile, could prove to be another vessel of vitality, a mirror in which the cosmos reveals that creation can wear many masks. If Titan's lakes are its heart, then its haze-laden sky is its soul, a planetary veil woven from light, chemistry, and time. No other world in the solar system wears an atmosphere quite like it. Thick, opaque, and luminous with orange light, stretching from the surface into space like a slow-burning flame. To look upward from Titan's surface would be to see an endless saffron glow. No stars, no sun, only the faint suggestion of day and night as shadows drift through a perpetual mist. Yet this sky, far from lifeless, is alive with complex organic chemistry, a place where molecules evolve from simplicity to near biological complexity. What happens in Titan's atmosphere is nothing less than a chemical symphony, a slow, cold reenactment of the prebiotic steps that may once have unfolded on the early Earth. Through the delicate balance of ultraviolet radiation, magnetospheric bombardment, and methane-nitrogen reactions, Titan's atmosphere becomes a factory of molecules, a continuous cycle of creation, transformation, and rain. Titan's atmosphere extends nearly 1,000 kilometers above its surface, making it the most substantial atmosphere of any moon. Structurally, it can be divided into three broad regions: The upper atmosphere, above 700 kilometers, is a region of plasma and photochemical reactions, where sunlight and energetic particles split methane and nitrogen. The middle atmosphere, 100 to 700 kilometers, is a factory of molecular synthesis, where radicals recombine to form heavier hydrocarbons and nitriles. Finally, the lower atmosphere, below 100 kilometers, acts as a distillation column. Aerosols coagulate, condense, and eventually fall as a fine organic drizzle. Each region has its own dynamics. The upper layers are turbulent, driven by solar radiation and the flux of charged particles from Saturn's magnetic field. The middle layers host haze formation, where polymers of carbon, nitrogen, and hydrogen, called tholins, aggregate into microscopic particles. And near the surface, these aerosols settle, forming fog, snow, and eventually deposits that shape Titan's landscape. Every molecule in Titan's air is on a journey, from photonic birth to chemical descent. A story of transformation powered by light but sculpted by gravity. For centuries, Titan's haze concealed its secrets. Even powerful telescopes could not pierce the orange shroud. Only with the arrival of the Cassini-Huygens mission in 2004 did the veil begin to lift. Cassini's Imaging Science Subsystem, ISS, Visible and Infrared Mapping Spectrometer, VIMS, and Composite Infrared Spectrometer, CIRS, revealed a multi-layered haze structure composed of organic aerosols, while the Ion and Neutral Mass Spectrometer, INMS, and Cassini Plasma Spectrometer, CAPS, detected a zoo of complex molecules high in the ionosphere. At altitudes exceeding 900 kilometers, Cassini identified positively and negatively charged ions with molecular masses exceeding 10,000 atomic units, astonishingly large for a planetary atmosphere. These ions likely represent long-chain polymers, precursors to macromolecules, and the seeds of the orange haze. Below, Cassini observed layers of aerosols descending like snow, forming multiple strata reminiscent of Earth's stratospheric clouds, but composed entirely of carbon-nitrogen compounds. The Huygens probe, during its 2-hour descent in 2005, provided the first direct measurements. Its instruments detected haze particles about 0.2 micrometers in size, coated in complex organics. The probe's optical sensors saw sunlight scatter through the atmosphere in a soft amber glow, confirming that Titan's orange sky is due to tholins, substances that absorb blue light strongly while transmitting red and orange wavelengths. It also measured a gentle drizzle of aerosols, falling continuously at a rate of several centimeters per 1,000 years. Imperceptible, yet relentless. Titan's atmosphere, it seemed, was not static, but constantly painting its surface with organic dust. At the root of Titan's haze is photochemistry, the interplay between methane, nitrogen, and sunlight. When ultraviolet photons or energetic particles from Saturn's magnetosphere strike methane molecules, they break apart into reactive radicals such as CH3 and CH2. These radicals combine to form ethane, C2H6, acetylene, C2H2, and more complex hydrocarbons. Nitrogen, meanwhile, is split into atomic N, which reacts with hydrocarbon fragments to form nitriles like hydrogen cyanide, HCN, and acetonitrile, CH3CN. As these molecules recombine and polymerize, they form increasingly complex structures, polywines, aromatic hydrocarbons, and nitrogen-rich compounds that absorb ultraviolet light. These act as nucleation sites for further condensation, leading to the formation of solid particles, tholins. Laboratory experiments have shown that tholins are chemically diverse, containing carbon chains, nitrogen heterocycles, and even oxygen-bearing compounds when trace water or carbon dioxide is present. Their color, texture, and spectral properties closely match Titan's haze, confirming them as excellent analogues. Tholins are particularly interesting because when dissolved in water or ammonia, they yield amino acids, nucleobase analogues, and carboxylic acids, the same basic ingredients that form proteins and DNA. On Titan, where water occasionally erupts from cryovolcanoes or impact events, these deposits could undergo brief aqueous processing, producing localized chemical evolution. Thus, Titan's haze acts not only as a screen, but as a seed bank of prebiotic molecules, ready to awaken when conditions allow. Titan's haze is not merely the product of sunlight, it is also charged and electrified. Cassini detected an abundance of negative ions, rare in planetary atmospheres, suggesting that electron attachment plays a major role in its chemistry. These ions can catalyze the growth of complex organics by enabling polymerization at much lower energies than would otherwise be possible. The presence of such charged aerosols transforms Titan's atmosphere into a plasma reactor, where molecules are continually built and rebuilt through electrochemical processes. Occasional lightning-like discharges, though rare, may further drive organic synthesis. Theoretical models show that electrical sparks in Titan's methane-nitrogen atmosphere can produce amino acid precursors in quantities comparable to the famous Miller-Urey experiment on early Earth. Even without lightning, cosmic rays penetrate deep into Titan's atmosphere, maintaining a steady supply of high-energy particles that sustain the haze chemistry. Titan, in this sense, is an autonomous factory of organics, powered by radiation rather than biology. Once formed, the aerosols begin their long descent. Over the course of months to years, they drift downward, colliding, sticking, and growing. As they reach cooler altitudes, they condense further, forming aggregates up to a few micrometers across. By the time they near the tropopause, around 40 kilometers, these particles have become complex, multi-layered structures, tiny globules of carbon and nitrogen wrapped in thin coatings of hydrocarbons. Gravity slowly draws them down, and they settle on the surface as a global drizzle of organic dust. The scale of this deposition is enormous. Models estimate that Titan's surface receives about 0.5 millimeters of organic material per year, equivalent to hundreds of millions of tons annually. Over geological timescales, this has built deposits several kilometers thick in some regions. The dark equatorial dunes detected by Cassini are composed primarily of this material, endless seas of tholin sand, sculpted by Titan's gentle winds. Each grain is a microfossil of atmospheric chemistry, an archive of billions of years of molecular evolution. When methane rain falls upon these organic layers, partial dissolution and reprecipitation occur, creating chemical diversity in the surface sediments. These interactions could generate localized pockets of semi-liquid organic slurries, what some scientists call tholinite muds, where reactions might proceed toward complexity. In such pockets, Titan could host transient chemical microhabitats, miniature laboratories of prebiotic synthesis. Titan's atmospheric haze is not entirely unique. Similar organic aerosols exist on other worlds, and even in the interstellar medium. The giant planets Jupiter and Saturn both exhibit hydrocarbon hazes formed from methane photolysis, while distant exoplanets with thick atmospheres may show similar features. On Earth, analogues can be found in smog or soot, complex organic particulates formed by incomplete combustion, or photochemical smog in the troposphere. What sets Titan apart is the scale and permanence of the process. While Earth's smog dissipates in days, Titan's haze has persisted for billions of years. It demonstrates that organic synthesis is a universal outcome of energy interacting with simple carbon-bearing molecules. Wherever methane and nitrogen exist under light, Nature constructs complexity. Titan simply provides the most perfect and enduring stage on which this cosmic chemistry plays out. The haze does more than color Titan's sky. It shapes its climate and weather. By absorbing sunlight and re-emitting infrared radiation, the haze regulates Titan's surface temperature, maintaining its delicate thermal balance. Without the haze, Titan's surface might be even colder. With it, the Moon experiences a mild greenhouse effect counteracted by high-altitude cooling. The interplay of haze production, methane abundance, and photochemical loss thus determines Titan's climate stability over geological time. This feedback loop is dynamic. If methane levels drop, less haze is produced, allowing more sunlight to reach the surface and increasing evaporation. A self-regulating mechanism akin to Earth's carbon cycle. Conversely, if methane rises, the haze thickens, cooling the surface and reducing evaporation. In this way, Titan's atmosphere may maintain equilibrium through organic feedback, a chemical counterpart to biological regulation on Earth. It is an elegant demonstration that stability can arise without life, a planetary system self-tuned by physics and chemistry alone. Beyond its immediate fascination, Titan's haze serves as a window into cosmic organic chemistry. Similar photochemical processes occur in the atmospheres of exoplanets, comets, and interstellar clouds. The same ultraviolet-driven pathways that produce tholins on Titan also operate in cold nebulae, creating organic dust that later seeds planets. In this sense, Titan's sky is a microcosm of the galaxy's chemistry, a living example of how simple molecules everywhere evolve toward complexity. Some researchers suggest that the earliest organic molecules that seeded Earth's prebiotic ocean may have formed through similar mechanisms in the solar nebula, then fallen to Earth within comets or meteorites. Titan's haze thus bridges the gap between astrochemistry and biochemistry, showing that the synthesis of life's precursors is not a miracle, but a natural, universal process. Wherever light meets carbon, complexity follows. To understand Titan's haze is to understand creation itself. It begins with the most basic ingredients, methane, nitrogen, and sunlight, and ends with molecules so complex they border on biology. Each particle is a story, born in starlight, transformed by chemistry, and destined to fall as snow upon alien seas. The entire Moon is enveloped in this slow rain of possibility. Titan's sky is not a static blanket, but a living archive, continuously rewriting itself through photochemical poetry. In that eternal amber glow lies a profound truth, that life's chemistry does not require warmth or oceans or oxygen. It requires only instability and time. Titan's haze shows that complexity is a cosmic habit, and that the universe, given enough patience, will always find ways to assemble order from chaos. When the next generation of explorers, robotic or human, stands beneath Titan's orange sky, they will be looking up not into emptiness, but into a sky alive with chemistry, a place where starlight and molecules collaborate to rehearse the ancient dance of creation. Titan reminds us that even in the farthest cold, the universe is still dreaming of life. On January 14, 2005, humanity touched another world of mystery. After a 7-year journey across nearly 1.5 billion kilometers, the Huygens probe, built by the European Space Agency and carried by NASA's Cassini spacecraft, detached and began its solitary plunge through Titan's thick atmosphere. For more than 2 hours it fell, breaking through haze, clouds, and methane mist, transmitting radio signals back to Cassini, and from there to Earth. Those faint pulses of data, traveling across the void for more than an hour and a half, would reveal a world unlike any other. A landscape both alien and eerily familiar. A place that looked like home, but was colder than Antarctica's heart. Huygens' descent remains one of the most extraordinary achievements in planetary exploration. It was the first, and so far only, spacecraft to land in the outer solar system, and the first to sample Titan directly. Its findings reshaped planetary science, deepened our understanding of prebiotic chemistry, and forever altered our conception of where life's story could unfold. Huygens entered Titan's upper atmosphere at 1,270 meters per second, protected by a heat shield that glowed brighter than any flame could in that frigid realm. At about 180 kilometers altitude, parachutes deployed, and the probe began its slow, spiraling descent through Titan's golden clouds. As its instruments switched on, Huygens began tasting and photographing a world that no eye had ever seen. Through its descent, Imager Charge Spectral Radiometer, DISR, Huygens captured the first color images of Titan's surface during descent, a breathtaking revelation of orange skies, faint sunlight, and a patchwork of dark and bright regions below. At about 40 kilometers altitude, cameras pierced the haze enough to show river-like channels branching across the terrain, converging into darker plains, unmistakably the signatures of erosion and liquid flow. Titan, it seemed, had rivers and floodplains sculpted not by water, but by liquid hydrocarbons. Simultaneously, Huygens' sensors recorded temperature, pressure, wind speed, and atmospheric composition. The data confirmed predictions. Titan's atmosphere was thick and nitrogen-rich, containing about 1.5 bar of pressure at the surface, slightly greater than Earth's. Methane accounted for around 5% near the surface, the lifeblood of its meteorology. The descent profile revealed a troposphere layered with methane clouds, their droplets condensing and evaporating as they drifted through a vertical gradient of cold and warmth. At last, after 2 hours and 27 minutes, Huygens touched down on the surface at roughly 5 meters per second, a gentle fall compared to its cosmic journey. For a few seconds, its cameras went blind, enveloped in methane mist raised by the impact. Then, slowly, the images came back into focus. Before it lay a landscape of rounded pebbles and cobbles, scattered across a plain that looked like a dried river delta. Some of these rocks were likely water ice boulders, hardened and shaped by flows of methane, their smoothness a testament to past rivers. The surface temperature was measured at -179 degrees Celsius, with a faint breeze rippling across the probe's sensors. The soil beneath was neither solid nor liquid, but soft and moist, yielding slightly before firming, suggesting a crust of icy grains coated with hydrocarbons, perhaps damp with methane. In one image, bright patches hinted at frost or wetness, possible residues from evaporated methane pools. Titan's ground was not frozen. Silent. It was dynamic, alive with traces of recent rainfall. For more than 72 minutes, Huygens transmitted from the surface until Cassini, dipping below the horizon, could no longer hear it. Yet, in that short time, it sent enough information to rewrite textbooks. The panorama it returned was haunting. A cold version of a terrestrial landscape, with horizons fading into amber fog, hills sculpted by erosion, and channels carved by liquid. The first images from the ground of Titan stunned scientists and philosophers alike. It was as though Earth had been transported to the edge of the sun's warmth and remade in methane and ice. As Huygens descended, its gas chromatograph mass spectrometer, GCMS, analyzed Titan's atmosphere, measuring isotopes and organic molecules. The instrument detected methane, molecular nitrogen, and traces of ethane, acetylene, hydrogen cyanide, and carbon monoxide. Crucially, it found argon-40, a decay product of potassium-40. proof that Titan's interior was geologically active, venting gases from within. This confirmed that Titan's methane was not primordial, but continually replenished by cryovolcanism or subsurface reservoirs, keeping the atmosphere chemically alive. The isotopic ratios of nitrogen and carbon provided further insight. Nitrogen's isotopic signature suggested it originated from ammonia decomposition, not from the solar nebula, meaning Titan's atmosphere evolved from internal chemistry rather than external capture. Carbon isotopes revealed a complex interplay between photochemical loss and replenishment. Together, these measurements painted Titan as a self-sustaining chemical world, recycling its atmosphere over geologic timescales. Another surprise came from methane's vertical distribution. Huygens found supersaturation at some altitudes, more methane vapor than would be stable, implying active convection and localized cloud formation. Titan's methane cycle was not just theoretical, it was meteorological reality, mirroring Earth's hydrological engine in an entirely different chemistry. Among Huygens' lesser-known triumphs was the detection of sound. Its microphones recorded the faint hiss of wind, the first audio ever captured from another world beyond Mars. The sounds confirmed a gentle breeze of about 1 to 2 meters per second, carrying tiny particles through the air, perhaps drifting flakes of organic snow. Later, scientists used the Doppler shift in Huygens' radio signal to reconstruct wind speeds and directions at multiple altitudes. The results revealed a complex pattern of atmospheric motion, east-to-west superrotation in the upper atmosphere, transitioning to calmer breezes near the surface. Titan, like Venus and Earth, possessed an active global circulation, redistributing heat and methane across latitudes. Even its winds were alive with chemical consequence. By transporting haze and moisture, they helped shape dunes, fill polar lakes, and maintain the delicate climate equilibrium that defines Titan's modern era. The images from Huygens offered planetary scientists their first direct glimpse of Titan's geomorphology. They revealed dark branching channels, hundreds of meters wide, converging into flat plains, unmistakable evidence of erosion by liquid flow. The team identified raised plateaus, valley networks, and possible sedimentary layering, suggesting long-term fluvial activity. Yet the channels appeared dry at the time of landing, implying episodic rainfall or seasonal flooding. The bright highlands corresponded to icy uplands, while darker regions indicated hydrocarbon-rich basins. The landing site itself, within the region called Adiri, appeared to be a transition zone between highlands and floodplains. Perhaps an ancient delta, where rivers once flowed into methane seas. The rounded rocks in the foreground were estimated to be 5 to 15 centimeters in size, their smoothness indicative of mechanical abrasion by flowing liquids. In every detail, Titan's surface mimicked the processes that shape Earth. Erosion, sediment transport, deposition, only with methane and ethane replacing water and sediment composed of ice. The revelation was profound. Titan was not a static frozen moon, but a planet in miniature, sculpted by weather and geology. Huygens' data hinted at a deeper narrative beneath Titan's crust. The measurements of argon-40 and methane supported the existence of an ammonia-water ocean beneath the surface, acting as a reservoir for volatile gases. Periodic upwellings or cryovolcanic eruptions could release these gases, replenishing the atmosphere and resurfacing the plains. Such activity would explain the relatively young age of Titan's surface, fewer impact craters than expected, and the persistence of methane despite photochemical destruction by sunlight. Beneath the icy crust, at depths of 50 to 200 kilometers, models predict a liquid layer kept warm by radiogenic heating and tidal flexing. In this internal ocean, water and ammonia could mix with dissolved salts, creating a medium far more hospitable to chemistry than the surface. Huygens' confirmation of active atmospheric renewal indirectly supports this vision of Titan as a layered, dynamic world. Solid ice above, liquid ocean below, and an organic sky above all. From its modest descent, Huygens yielded immense lessons about habitability. It demonstrated that complex weather, active geology, and rich organic chemistry can coexist far beyond the traditional habitable zone. Titan showed that life's potential does not depend solely on sunlight or warmth, but on energy flow, chemical diversity, and environmental cycling. By revealing a methane-based hydrological cycle, Huygens confirmed that Titan possesses all three, the same triad that sustains Earth's biosphere. While Titan's temperature makes terrestrial life impossible, it may host exotic chemistry or even methane-adapted organisms at its surface, and potentially water-ammonia life in its subsurface ocean. The boundary between biology and chemistry, once thought clear, now blurs under Titan's amber skies. Equally important, Huygens proved the universality of planetary processes. Rivers, rain, erosion, and cloud formation are not uniquely earthly phenomena, but expressions of physics. The cosmos, it seems, repeats its patterns with different materials: water on Earth, methane on Titan, nitrogen ice on Pluto. The implication is staggering. Planetary diversity may be vast, but planetary behavior is universal. Beyond the data, there was something profoundly human in Huygens' journey. It was a machine built by many nations, launched by Cassini's might, and guided by centuries of curiosity. As it descended through Titan's haze, its tiny sensors carried not just instruments, but the collective dream of understanding our origins. When its final signal faded, scientists around the world fell silent, aware they had just glimpsed a new chapter of the solar system's story. The images returned by Huygens remain among the most haunting in planetary exploration. They show an alien delta under a dim orange light, a world frozen yet active, silent yet eloquent. In them, we see Earth's processes mirrored in another chemistry, a reminder that the cosmos repeats its themes like variations on a symphony. Titan is not strange. It is familiar made foreign. The data from Huygens still fuel planetary science today. They inform models of Titan's climate, chemistry, and interior structure, providing the foundation for future missions like Dragonfly, which will explore Titan's surface from the air in the 2030s. Every planned experiment, from sampling dunes to measuring isotopes, builds on the groundwork laid by Huygens' short, heroic descent. The probe's legacy extends beyond Titan. Its success demonstrated that complex missions can thrive in the outer solar system, inspiring designs for landers on Europa, Enceladus, and even Neptune's moon Triton. It taught engineers how to communicate through dense atmospheres, how to build instruments for -180 degrees Celsius environments, and how to design parachutes that open in alien skies. Most of all, Huygens proved that exploration is an act of patience. 7 years of travel, 2 hours of descent, 72 minutes of transmission. And yet those fleeting minutes revealed a new world. The return was immeasurable. From Huygens, we learned that Titan is not a frozen relic, but a living world of chemistry. Its atmosphere is dynamic, its surface shaped by liquid, its interior still active. We learned that organics form naturally from methane and nitrogen, that they rain from the sky, and that they collect in lakes and plains, all without life's intervention. Titan showed us how the building blocks of biology can arise spontaneously, given the right balance of energy and time. We also learned humility. In that distant descent, we glimpsed a version of Earth long before life, or perhaps long after it, a planet in chemical twilight, waiting. Titan reminded us that creation is not a one-time event, but an ongoing process, repeating itself across the cosmos in different forms. Its lesson is both scientific and spiritual. that the universe does not merely allow for life, it yearns toward it. When the last signal from Huygens faded, Titan reclaimed its silence. But its secrets had already crossed the gulf between worlds. They whisper still, in data, in memory, and in the imagination of those who will one day return. For most of scientific history, the search for life beyond Earth has been guided by a single axiom: follow the water. Water is the solvent of life as we know it, the matrix of metabolism, the medium of molecular exchange, and the foundation of every terrestrial biosphere. Yet in the frozen twilight of Saturn's realm, Titan has quietly shattered that assumption. Here, under a sky of methane and nitrogen, life's familiar chemistry is replaced by something new, a living system of hydrocarbons, nitriles, and cold energy flows that mimic biology in structure and function, if not in composition. Titan forces us to confront a deeper truth, that habitability is not a formula, but a spectrum, and that life may be not the exception, but the inevitable outcome of chemistry, wherever it finds balance. When planetary scientists first coined the term habitable zone, they imagined a narrow belt around a star where temperatures allow liquid water to exist. Earth sits comfortably within this zone. Mars grazes its outer edge. Venus lingers near its inner boundary. Beyond this line, it was assumed life could not persist, too cold, too dark, too inert. Titan has overturned this paradigm. Though it orbits 1 billion kilometers from the Sun, bathed in light, barely 1% as strong as Earth's, Titan sustains an active hydrological cycle, albeit one based on methane instead of water. It has clouds, rain, lakes, and erosion, all powered by a distant, diminished sun and internal heat. In doing so, Titan has forced us to redefine what habitable means. Habitability, we now realize, is not bound to temperature alone, but to energy flow and chemical potential. Any world that maintains liquid of some kind, a stable atmosphere, and gradients of energy, be they thermal, chemical, or electrical, possesses the essential ingredients for complexity. Whether that liquid is water, methane, or ammonia becomes secondary. The universe in this light is not sparsely habitable. It is richly adaptable. This redefinition transforms the habitable zone from a narrow ring into a vast multidimensional field, spanning the icy moons of the outer solar system, the atmospheres of exoplanets, and perhaps even the clouds of gas giants. Titan stands at the threshold of this expanded view, a cold archetype of alternative life chemistry. From its atmosphere to its crust, Titan satisfies the 3 great conditions for life's emergence, though in forms alien to us. Energy. Titan receives energy from multiple sources: weak solar radiation, Saturn's magnetospheric particles, cosmic rays, and internal heat from radioactive decay. These sources drive continuous photochemistry, producing hydrogen, acetylene, and organic radicals that store chemical energy. Even at minus 179 degrees Celsius, reactions proceed slowly but steadily, maintaining a dynamic equilibrium that never quite freezes into stasis. Solvent. Titan's lakes and seas of liquid methane and ethane provide a medium for chemical exchange. Though non-polar, these solvents allow hydrocarbons and nitriles to interact, stabilize radicals, and form long-chain molecules. In Titan's subsurface ocean, water and ammonia may coexist, adding a second solvent system, one cold and hydrocarbon-based, one warm and aqueous, possibly exchanging materials through cryovolcanic vents. This dual-solvent world blurs the boundary between Earth-like and exotic biochemistry. Stability. Titan's dense nitrogen atmosphere and global haze insulate the surface from radiation and micrometeoroids. Its thick blanket of organics shields the lakes from ultraviolet destruction, allowing chemistry to persist over geological time. The result is a planetary laboratory of slow evolution, where molecular complexity accumulates, awaiting the right trigger for self-organization. Together, these three factors form a framework for universal habitability, one that transcends temperature or composition. Titan demonstrates that life does not require Earth's conditions. It requires Earth's principles: energy flow, molecular diversity, and time. Astrobiology is now undergoing a philosophical shift. For decades, missions were guided by the search for liquid water, the presumed prerequisite for life. The mantra, "Follow the water," drove exploration of Mars, Europa, and Enceladus. All promising and logical targets. But Titan, with its alien seas, has expanded the scope. The new frontier is follow the chemistry. Wherever energy sustains chemical disequilibrium, complexity will follow, regardless of solvent. This transition represents a maturation of thought. Life is not an element of chance, but a continuum of complexity. In this continuum, water-based life is merely one branch: fast, dynamic, and oxygen-rich. Methane-based life would be slower, colder, but perhaps longer-lived. Ammonia-based life could thrive in deep, sub-zero oceans. Even sulfuric acid life, as hypothesized for the clouds of Venus, may exist under extreme conditions. The defining feature is not the medium, but the pattern of self-organization that emerges within it. Titan, more than any other world, anchors this new philosophy in observation. It provides the experimental evidence that chemistry can remain active under cryogenic conditions, sustaining cycles, weather, and molecular growth. It teaches us that the quest for life must be inclusive of diversity, not bound to Earth's precedent. The continuum of worlds. With Titan as our guide, we can now see the solar system as a continuum of chemical environments, each testing a different variation of habitability. Earth represents the warm, oxygenated end, dynamic, fast, and teeming. Mars offers a marginal case, once wet, now dry. Its atmosphere thin but chemically rich. Europa and Enceladus hide oceans beneath ice, warmed by tidal flexing, their waters salty and dark. Titan stands at the far end, a world of hydrocarbons and haze, cold yet alive with chemistry. Between these extremes lies a spectrum of possibilities, suggesting that habitability is not a binary state, but a gradient of potential. The same universal laws, chemistry, energy balance, fluid dynamics, apply to all. Life may simply represent one expression among many of these principles, arising wherever the universe permits complexity to persist. Titan's place in this continuum is crucial because it expands the boundaries outward, into the frozen realm of giants. It reminds us that the search for life must include not only the temperate worlds, but also the frozen, the distant, the unearthly. The lessons of Titan ripple outward to the stars. Thousands of exoplanets discovered by missions such as Kepler and TESS reveal a vast diversity of worlds: super-Earths, mini-Neptunes, ocean planets, and cold gas giants with moons. Many orbit red dwarf stars, where ultraviolet light and flaring activity can drive photochemistry similar to Titan's. Some may even host thick atmospheres rich in methane and nitrogen. Exotitans, analogues scattered throughout the galaxy. Understanding Titan's chemistry allows scientists to interpret the spectral fingerprints of such worlds. The presence of organic haze, for instance, could obscure surface features and mimic biological signatures. By studying Titan, we learn to distinguish between abiotic complexity and genuine biosignatures. Conversely, if methane-based life exists on Titan, its spectral imprints could guide the detection of similar life elsewhere. In this way, Titan serves as both laboratory and template. teaching us how to recognize the chemistry of habitability across the cosmos. The universe may be full of Titan-like worlds, cold, orange, and alive, with slow-burning chemistry. Their skies may glow dimly, their lakes ripple gently, and their atmospheres whisper the same ancient molecular story that Titan tells us today. The more we study Titan, the more it challenges the very definition of life. If Titan hosts organisms built from methane and nitriles, what would their metabolism be? How would they replicate information without DNA or proteins? Could consciousness or evolution arise in such a slow chemical realm? These questions blur the distinction between life and non-life, forcing us to ask whether life is chemistry animated by energy, or something more elusive, a pattern of self-preserving order that the universe naturally tends toward. Some philosophers of science now suggest that life should be defined functionally, not compositionally. Life is a system that maintains itself far from equilibrium by harnessing energy and preserving information. By this definition, a methane-based organism, a plasma structure in a gas giant's atmosphere, or even an autocatalytic crystal could qualify. Titan thus becomes a philosophical as well as scientific frontier, a test case for the universality of living systems. If Titan's chemistry crosses the threshold into true metabolism, it would mean that life is not rare but inevitable, a natural phase of matter under the right conditions, much like crystallization or magnetism. The cosmos would then be viewed not as a dead expanse, but as a vast chemical ecosystem, perpetually experimenting with ways to organize itself. In this new paradigm, water-based life is one instance in a grander taxonomy of cosmic biology. Titan represents the methane branch, Europa and Enceladus, the aqueous branch, and other moons or exoplanets may represent ammonia, formamide, or hydrogen sulfide branches. Life, in this view, is the universe's way of converting energy into information, matter into meaning. Every solvent becomes a dialect, every world a variation on a single theme, order emerging from chaos. The recognition of this broader canvas does not diminish Earth's uniqueness, but situates it within a cosmic lineage. We are not the exception. We are the local expression of a universal impulse. Titan's frozen seas and organic clouds are the next verses in that ongoing cosmic poem. When we imagine future explorers, perhaps robotic at first, human later, standing on Titan's shore, gazing across Kraken Mare under an orange twilight, we are not just imagining a distant scene. We are witnessing the expansion of human thought itself. The discovery that life can exist without water would mark one of the deepest intellectual revolutions since Copernicus displaced Earth from the center of the cosmos. It would remove humanity not just from spatial centrality, but from chemical centrality, proving that even life's substance is not unique. In that moment, biology would become a cosmic discipline, and the word habitable would lose its anthropocentric limits. The search for life would cease to be a quest for Earth's twins and become a quest for chemical kinship across the stars. Titan teaches us that habitability is not a place but a process, a continuous negotiation between energy, matter, and time. It shows that nature's creativity does not stop at the boundaries of our understanding. It transcends them. Life, as Titan suggests, is not a fragile accident, but a universal tendency toward complexity, expressed differently on every world. In the silence beneath its orange sky, Titan whispers a truth both humbling and exhilarating, that the universe is not waiting for life. It is becoming life, everywhere, in every possible way. When we finally grasp that, we will understand that the search for life is not about discovering others. It is about discovering ourselves in the chemistry of the cosmos.